and some part of the speaker's work. The theory is by no means complete. However, we are going to discuss not itself today. I'm going to discuss not itself, but its generalizations. As for the word crazy, you see written in red, it tells us that I'm not really responsible for the suggestions I'm going to make. Maybe some of them are not really doable, but as you see at the bottom of the screen, maybe not we, but our students or our students will do something in these or other directions. Okay, now, my generalizations are split in two parts, and the first part is what can be called the obvious ones, and I'm going to list them very quickly. The strategy is more or less as follows. So, but before I formulate it, you see the benefits of the equivalence of categories with very different objects. One of the applications of this difference is that some operations in one category that seems to be quite natural is strange in other one. I give two examples. In the category of dessins d'enfant, we easily, there is a natural operation of contracting an edge or deleting an edge. It should mean something in the equivalent category of Belyi pairs, and we really don't know what. In the opposite direction, there is a question on which we work for several details. On the right-hand side, on the category of Belyi pairs, the action of absolute Galois groups is defined. And what we are interested in, I mean, we starting from Alexander Grothendieck, who invented the whole theory, we are interested in the Galois orbits of the sense that we understand as a tool for visualizing the absolute Galois group. So in the first kind of generalizations, we just relax some restrictions and see whether there is a chance that some of these transferring of operations survive. So it does not work. I don't know why. So the first obvious one is the following. When we allow our largest component to be singular, here is a small motivation for that. So at the end, we are going to discuss the straightforward many-dimensional generalizations, but together with having this filtration with x sub n, the largest term, we can consider the trivial case of n equals 1. And we, just thinking for a while about it, we see that It is simply the graph theory, the theory of such topological manifolds, topological spaces that the complements to a finite set are disjoint union of intervals. Turning to the next case from the other side, we understand that we need something like that, but x2 in the three-dimensional case is no more a manifold. It can be something like a graph. Basically, it means that it is a singular surface, possibly highly reducible. However, under some assumptions, these singularities should have and do have some algebra geometric meaning, so they are just stable curves, and the basic theory has to be generalized to cover the stable curves as well. And there are some papers by Amburg and Kreines about it, though perhaps something more has to be done. The next direction is related to weakening the restrictions to the complement of the graph on surface. So now we allow it to be the disjoint union, not only disks, but of annuli as well. And there is a proper mathematic context for that. In the Strebel pairs producing such structures. So in this case, the Belyi pairs should be replaced by Strebel pairs that, unlike Belyi pairs, cover all the possible curves, x's, and then x1 is the critical graph of the horizontal variation. Well, the last part of this slide can be understood by those who understands this famous decomposition of moduli space of Jn over complex numbers, the decomposition of the author, which is difficult to specify. However, a very complicated moduli space with marked points times the octant turns out to be the union of the real octants labeled by dessins, that 3 means with the valences of vertices at least 3. Then there is an n capital means both marked points on the curves and number of disks in the complement of the graph of the descent. And there exists a discrete Mulasi-Penkawa version of it that belongs completely to arithmetic, as you see. So maybe I should stress that in the right-hand side we have the point in the right-hand side is a metrized ribbon graph. That is with real, that is a ribbon graph that is the same of the Sandalphon with a positive real length of all the edges. When we discretize everything, we get a completely parallel structure. However, it works only for marked moduli space. It is still unknown for the pure moduli space, that is for n capital equals 0. And I now express a hope that maybe the suggested structure 2 can help in constructing something similar to the case of positive n capital. The next thing is about Fried families, where we replace the number of critical points of Belyi pairs from 3 to 4, and for some years I have written a lot and published something and talked a lot about it, so I basically skip it, though mentioning a very important feature of this realization. We have the theory of descent d'enfant and Belyi pairs on the basis of Fried family. Well, for those who maybe I didn't hear about this theory, I stress that the Belyi pairs are rigid objects, while the Fried pairs, the object with 4 marked points on the projective line, have a continuous parameter, the cross ratio of these critical values. So Fried pairs come in families, and well, just the cross ratios of the critical values form the Belyi function on the base. So, well, this object is defined and, as I write in large font, discussed a lot. However, we have not sufficient understanding of it, so it also belongs to mathematics of future. Well, the next one is one of the most straightforward. The theory of Belyi pairs without descent d'enfant is a purely algebraic object and therefore can be studied over any field. So it is well studied over the algebraic closures of finite field by Bogomolov, Zapponi, and many other people. I don't think I have met any considerations over the algebraic closure of the field of rational functions in one variables. So in these considerations there are no descents, but the third component that I'm not discussing today should work in all the cases, especially in the one that awaits. Now, just really a couple of words about the transcendent versions. The analogues of a Belyi function, the prototype is just a cosine function, about which we understand that it is an entire function which shares the main property of so-called Shabat polynomial in having exactly, the cosine has exactly 2 finite and critical values. And there exists very interesting theory of other objects like that. And well, I am aware of the papers by Bishop and Yeremenko, and there are some others. So that's all for our brief generalizations. So my recommendations were to stop at this point. However, again, very quickly, I mention two, I would say, non-trivial things. Just one general remark. In a very straightforward manner, we can consider these general perturbations of an arbitrary topological manifolds marked this with here with a black star. And well, we have something like a definition of successful theory, and the question is whether we have a chance to get something interesting in such a generality. I suppose that no, just because it is too general, and basically these black stars are in one-to-one correspondence with just cell decompositions of topological manifolds that become terribly numerous starting from a dimension 3. However, I have some suggestions for in dimension 3. So consider our constructions as we see it. And now Hegar, I'm not sure in my pronunciation of this mathematician in Russian, he's pronounced it like Hegor, and something like that is correct for this Danish name. So according to Hegor theorem, any three manifold can be split in two handle bodies related by an oriented reversing homeomorphisms. So if we apply this theorem to our three-dimensional descent, we find out that we have a complex structure on x sub 2 defined by x naught and x1. So here I'm using the bold x for that. So the this three-dimensional descent provides three manifold split by a Riemann surface with a complex structure on it. And it is such structures with the handle bodies are related to huge domains of arithmetic. Perhaps it started from my second teacher, Yuri Lanchmanin, in 1991, with the paper, the title of which you see. One of the arithmetic theories, besides the Radcliffe geometry, is the theory of Mumford uniformization. That is always also like the theory of descendant form, full of graphs. And I hope we find the direct relations of these several theories. And again, just really a couple of words about dimension 4, because here we have very straightforward generalization of the usual Belyi pair, though the concept of small branching in this case, when we consider complex surfaces instead of curves covering projective planes, a plane instead of projective line, it is not defined properly and in unique way. So there is some literature, and I want to mark especially interesting one. Some years ago, when my first teacher, Khoroshkin, was just 60, to him, Herzog devoted to him his study of cyclic covers branched over the arrangement of line. Some of these covers have the invariants that are extremal in the Bogomolov-Neyoka theory, from which one sees that the corresponding covers of certain nice arrangements of lines are vectors of the ball. Therefore, they seem to be the examples of the true animals. So I stop here. My conclusion is very short and maybe very appropriate, being pronounced by a 70-year-old mathematician. And thank you. And we have 4 minutes for the questions, so or remarks. So any questions, please? Now I change my
First to clap hands.
to the chairman of the session. Thank you. So questions or remarks? Perhaps I have to apologize for this talk from the point of view of its brevity. Only in the process of preparing it, I have understood that I need at least a couple of hours to tell what I'd like to. Okay.
Yura.
Yes.
Hi, so happy happy birthday. First, second, the question is, so for the handle bodies, we have just a generalization of quasi-Fuchsian group description.
Yes, these are the first ones. Yes.
And it still admits a sort of triangulation. Also, it's not no more triangulation. So that's triangulations where the shear coordinates or parameters are complex numbers. So we have embedding into SL2C, not
yes,
SL2R.
SL2C is the main hero of this conception. Yes.
Yes. So how it is related to this construction? Or is there any relation at all?
Yes, Leonia, thank you. The answer is rather long, and the whole theory, and it can be found in the Manin's paper I have quoted. Well, the brief answer is that they are related in terms of Briouat's complex. So the SL2, well, sorry, I'm not sure about triangulations. What I'm sure about is about, well, graphs that occur. Briouat's buildings are graphs, and the SL2C factored over the maximal compact group that gives the hyperbolic 3 space is similar to the p-adic SL2 with the subgroup of SL2 over integer, over p-adic integers. And the analogy goes quite far and is consistent with Arakelov geometry. So all of this can be read off Manin's paper. I'm not really sure that I have answered Chekhov's question, but we have now time for other questions. So sorry, we stop.
It's fair enough. So it's I remember, yes, I remember lectures. I actually attended lectures by Manin those years about hyperbolic geometry and this relation to Arakelov stuff. Was very fascinated.
Yes, Yes, I'm not sure that this idea was developed enough. Hello, Yulik. Unfortunately, we have started without you. I mean, I chaired instead of you. Maybe you are going to do it instead of me now. So we are just in 10 minutes retard. And I'm happy to invite Nikolai Adrianov for his talk.
I guess most of us here at this conference know that George Shabat is not only a mathematician but also a teacher, and there is quite famous in certain circles that he leads a club of experimental math since already almost 40 years. The club of experimental math is a mathematical circle for school children. When George attracts children to mathematical research based on making experiments with mathematical problems. And it's not only pedagogical experience, but also George and his students and I as well exploit experimental approach in our mathematical pursuits. Of course, it's not exceptional. Many mathematicians consider math as experimental science. I would like to mention a great book by Barway and Belyi, Griffiths on experimentation and mathematics. There is also a book by Vladimir Gurvich, Experimental Math. And probably most exciting example of experimental result is the Euler's pentagonal theorem, which was conjectured. The relation that was found by pure experiment and proved as this theorem much later. I'm going to tell today about some experiments and it will be somehow related to Euler's eta function at some point. We are talking about dessins enfants. I expect that most of us know what it is. It's a graph embedded into oriented surface, such that cutting the graph we get a number of cells. Of course, it's famous object most people know as bicolored map. I always will reference bicolored version of dessins enfants. And dessins enfants is a term invented by Alexander Grothendieck, and usually we use it to underline connection with Belyi functions and with Gauss action. But today I'm going to talk about pure combinatorical part, about pure combinatorical considerations. So for dessins enfants, we have a passport, which is a triple of partitions of n. N is number of edges of the design. These partitions are coming from degrees of white vertices, black vertices, and faces of the design. Here are just two examples of two designs of genus 0 drawn on a sphere or on a plane. And one of the questions which we are interested in is the number of realizations of the passport. So we have a passport. How many designs, different designs with this passport are there? To calculate such numbers, I personally use group theoretical approach. We can encode designs using permutations. just label the edges and the rotation around vertices, black vertices, white vertices, and faces. We get three permutations which give identity as a product, and the cyclic structure of these permutations is the components of the passport, and this group should be transitive. So this is just a way to think about these Anton funds. It's also important here to remember about automorphism group of the dessins, because when it is not non-trivial, then there are n factorial divided by automorphism size of automorphism group to get the number of different ways to label edges. And there is well-known formula by Frobenius, which enables us to do calculations, to calculate the number of dessins using irreducible characters of the group G, where group G is the group generated by these permutations, but we can consider it all as elements of Sn symmetric group, and consider the sum over irreducible characters of symmetric group. Well, actually we get not a number of dessins, but a weighted number of dessins. I mean that we get a number, sum of a set of realizations, sum of 1 divided by size of the automorphism group. Well, it's quite common knowledge that it's a proper way to count combinatorial objects dividing them by automorphism group, or by labeling, by marking these objects in such a way that these marks kill automorphism groups. If we do it this way, we get nice enumerating formulas. If we try to count pure counts, the formulas are not so nice. So it's a good formula. The only problem here that this formula will give a number of disjoint dessins, enumerate triples of permutation that generate non-transitive groups, but it's possible to make some programming to exclude these disjoint dessins and to get what we need. So I'm going to count the numbers, weighted numbers of passports, of realizations of passports, which are either regular of genus 1. It's well known that there are 3 types of regular dessins on or regular passports of genus 1, and also what I call almost regular elliptic passports. These are passports which are very close, look much like regular, but they different from them in small number of elements. I would like to notice that when I say almost regular elliptic passports, it means that this passport can be of genus 0, 1, or 2. It's not limited to genus 1. The genus of this passport is equals to the genus of the starting passport, P0. So we start from one small passport, and we get a sequence. We get a sequence of passports, and we want to compute the weighted numbers of realizations, and we get we get a sequence of rational numbers, because the sum is taken of 1 divided by automorphism group. So in general, it's a sequence of rational numbers, but we can multiply by something, to get a sequence of integer numbers. So here's the plan of our experiment. Let's take just one starting passport, small passport, one of three regular extensions, three regular types of genus 1, compute the numbers, multiply by something to get integer sequences, and look up this sequence in the online encyclopedia of integer sequences. And it turns out that in many cases they find this sequence in the encyclopedia, and we are glad to see it there, to read about wonderful mathematics which goes with these sequences. Well, and experimental maths means that you get some results, you make conjectures, you make some guesses, but you need to prove it as well. And sometimes it can be done easily or quite easily. And sometimes I have no proofs for experimental results. I will just state them as conjectures. So I will start with some well-known statements about dessins with regular passports. And regular passports doesn't mean that the design is regular. It doesn't necessarily mean that automotive group is transitive on the edges. So here I present two types of statements. We can calculate all dessins with given passport. Well, actually, it's about. Okay, next slide. I will explain what it's all about. You see, it's all well-known sequences. We get here three well-known sequences. Here are they expressed as sums of divisors or number of divisors with certain properties, divisors of n. But also you can look up online encyclopedia to see that it's related to beta functions, modular forms, and so on. I will just briefly explain how we get this sum for non-regular dessins, how we get these enumerative results, that number of weighted realizations is the sum of all divisors of n. Well, we are talking about sublattices of two-dimensional lattice. Well, here's an example on square lattice, but it doesn't matter. It also can be triangle or hexagon lattice. Any sublattice can be, in any sublattice, we can choose a fundamental parallelogram such a way that one of its edges is horizontal, and so it's a D. D is a divisor of n, and for each D we have D ways to skew take rectangle and skew it to get D other fundamental regions. And as you see here, it's taken from online encyclopedia. The generating function of this sequence can be expressed via Euler's eta function. And the regular dessins, they correspond to square lattices, square sublattices, so it's also a well-known topic. It's a number of representations of n, as we should be accurate here, as a number of, as representation n as a sum of at most two non-zero squares of natural numbers. Okay, here we have Jacobi eta function. So it was all well known, it's a common knowledge, nothing new I told you here. now we are moving on to almost regular dessins. Some simple cases for now. We start two statements about almost regular dessins of type 333. As you see, so here the passport has exactly three special numbers. In this case, it's 111 or 3 ones in the first component of the passport. All other components of the passports are equal to 3. So what we can do with these designs, actually these are passports of genus 0. And we can consider the cover of projective, consider a design on a sphere, and consider free branch, degree of free covering of the sphere branched over 3 points. And pulling back the design, we get a design on a torus of genus 1, and this design is regular, while all passport is all 3s, and also there is automorphism for the 3, which has branching points. So it explains that it's actually about we get a regular design. So it means that the regular design with how many edges? Well, in first case, it is a regular design with 3n by +1 edges, and in the second case, it is the regular design with 3 by n edges. So we already have formulas for regular designs, and oops, here it is, the last line of the slide. And the two sequences that we discuss here are just subsequences of the sequence that we had on the previous slide. So these sequences are new. At least first sequence is new, is different from what we had at the moment, but they are just subsequences. They have separate. They have their own ID in the online encyclopedia, but actually it's just a subsequence. Well, if we go to move on to 244 designs, then the same maybe same considerations apply. And there are some passports which we can consider, which have 3 distinguished points, and we consider branched cover of degree 4, which is branched over, has branches of degree 2 over first one, degree 4 and degree 4, so that when we pull back the design to the torus, we get a regular design. And again, these are just subsequences. In this case, we have 3 subsequences of the famous sequence, which enumerate these kinds of passports. That's not the end of the story for these types of design. 244.
Just you're speaking 20 minutes.
10 minutes. Oh, thank you much. In this case, it's also possible to get designs, almost regular designs, by factoring any design with regular passport, not necessarily regular design, just having a regular passport. This design has fundamental area parallelogram, and it always has automorphism, non-trivial rotation with branch points, which gives factor by cyclic group of order 2. And so we can get a number of results from here. It's not so trivial, because here it depends on the oddity of d and n by d. As I explained already, the fundamental parallelogram, we know how they look, and if we accurately count different types of branch points, here are 5 types. It's 5 types of branching, and each type can be obtained from 3 different situations. So we get not so trivial functions here. At least here are two new sequences, really new sequences, which are not subsequences of what we had earlier. Sums of these divisors of n such that n by d is odd. Very nice sequence. Okay, yes, and we can count and just sum the results for every row. Well, same applies to the third type of the regular passports. I will skip it, but you can see that there are 13 different formulas, 13 different sequences which we can get and prove results here. Well, it's not the end of the story, because there are many other passports which produce very nice sequences, and we have at least I do not know any simple geometric explanation like in the previous cases, which can explain these formulas. So I will just show some of these formulas. This for 3, 3, 3, and let us note that here this sequence actually is this generating function is actually the 4th power of some sequence, and this is the 5th power. Actually, here is just an attempt to continue this list. And yes, it happens for several occasions, but it stopped at this point. And here and further, the equality doesn't hold. Same for quadratic lattices, quadratic passports. I would like to show here that we again get the same sum of d such that n by d is odd. But you see here the passport, the 3 in the passport means that you cannot cover it and get a rectangular design. And I have no proof of all of these statements. My student Veronika Triumova is going to defend her undergraduate student is going to defend her work about calculating one of these passports, but the result is not, we are quite close. We get some combinatorial considerations and some combinatorial recurrences, but not proof of this formula. So here we again can see that some sequences are just there. Nice sequences. These are some number of representations of n as sum of 2 triangle numbers, of 6 triangles numbers, 10 triangle numbers. Actually, it means that it is the power of some trivial generation function. And also it stops at 717. And so on. I will show you, just skip several slides where the same conjectures are made about 2, 3, 6 type passports. Well, I just shown the sequences which I found in online encyclopedia, but there are also some other sequences which are not found in online encyclopedia, but they look very nice. For example, this is a sequence which looks like very close to sequence of n squared. With some differences, 9 here, 25 here. So let's write it as an n squared minus something. And minus something is -1, -4, -9, -15, -25. Again, something very close to squares. So I believe there is a good explanation, good enumerated formula answer to this. Well, here we get double sequence, which looks much like the previous one. And some more on other slides. I have to stop now. Just that this is the last my slide. And of course, we need to get proofs. It's not easy. Combinatorial attempts, which we had just for one sequence, is elaborate. And there are a lot of questions with much less answers. So we had a lot of beautiful formulas when this source of beautiful formulas will stop. For how many edges, or maybe for going to genus to and higher. All these formulas are somehow related to theta functions. Well, actually, it's not so surprising. Many combinatorial things are enumerated using combinatorial functions. We saw many different sequences, different passports produced sequences, the same sequences. So the natural question is there natural bijective correspondence between these sets? So I didn't mention the Galois section and relation to Belyi function and Galois group. Nonetheless, I want to come back to this, and if we, my question is, if we consider Galois action on the dessins, on these types of dessins, probably we get some orbits of the Galois group. So the question is the structure of the numbers, which are expressed, sometimes are expressed as the sum of divisors. Do they reflect in the structure of Galois orbits? That's all. Thank you very much.
Thank you. Well, unfortunately, we have no time for other questions. However, this evening we'll have a general discussion when we can express our feelings. I'm going to do that. Now, I'm happy to invite Gareth Jones for his talk. Please, Gareth.
Thank you, George. I'm just sharing screen. Okay, good. Well, first of all, happy birthday, George. Congratulations on achieving 70. I've known you for about 30 of those 70 years, and your work has been a great source of inspiration to me, particularly at a time about 30 years ago when I was looking for a new path in mathematics, and you showed me a very beautiful path to follow. The first two talks this morning have given a promise that maybe the next 30 years will also be just as exciting. I look forward to enjoying at least another 30 years of work on design platform, and I hope you do as well. What I'd like to talk about today is joint work with.
Sorry for interrupting you, but I have to remind you that at your 65 celebration, you have just invited everybody to your 100 years. So it's quite.
I hope you're all of you are there. This is joint work with Gabor Gevai. We did it in the last 6 months or so in terms of maps on surfaces, because that is a common language which we share, but it can also be translated into the language of design. And in fact, that was my eventual intention in doing this. So what I will describe is just a partial theory which works for clean design, and I hope to be able to generalize it with Gabor to all design later. So let me start with something very elementary. We often notice in mathematics that two objects may have isomorphic symmetry groups. And sometimes this means that there is a connection between the two objects. Sometimes it does not. And here's an example. We all know that the alternating group A5, it's the rotation group of 3 regular polyhedra, the icosahedron, dodecahedron, and the great dodecahedron. Now we know that the icosahedron and the dodecahedron are closely related. They are duals of each other. But what about the great dodecahedron? Where does this come in? Well, there's a very simple construction which takes the icosahedron and changes the cyclic rotation of edges around the vertices while preserving the graph. So in the case of the icosahedron, if we take this vertex, then the cyclic rotation of edges goes 1, 2, 3, 4, 5. But if you take the square, or if you prefer double of that rotation, then you go 2 steps around, you go 1, 2, 3, 4, 5. And this gives you the faces of the great dodecahedron. You get pentagonal faces appearing, joining up the edges of the same graph. And this gives you a new design. It's the great dodecahedron. It's on Bring's curve of genus 4. It has the same automorphism group A5, which is of index 2 in the automorphism group of the curve. If you do the same operation again to the great dodecahedron, you get back to the icosahedron. So there's an involution here connecting the icosahedron and the great dodecahedron. And I've drawn a little graph at the bottom to express the relationship between these 3 designs, the dodecahedron, the icosahedron, and the great dodecahedron. The first 2 are related by duality, and that's represented by this broken edge. And the second 2 are related by this squaring operation with an unbroken edge. Now, so you can think of D and H2 as being permutations of these 3 regular designs. Now, our aim is to investigate the corresponding graphs which would describe the regular design for an arbitrary finite group. And just to make life easy, we restricted our attention to clean design, or equivalently orientably regular maps. But the hope is to extend this to all design. This brings in a lot more design. For example, for A5, I've shown you the 3 clean design, but there are in fact 19 regular design. So you'd have a graph with 19 vertices and many more edges. Let me just briefly summarize the basic ingredients. We've seen them already in Nikolai's talk and in George's talk. I'm talking about Belyi pairs. You have monodromy permutations over the 3 critical values. These are permutations of the sheets. Their product is 1. They generate a monodromy group, a transitive group of degree n. The design is a bicolored graph embedded in the surface with black and white vertices over 0 and 1. And their valencies are just the cycle lengths of the permutations x and y. I'll restrict attention to regular design, those for which the automorphism group is transitive on the edges, and also to clean design, where y has cycles all of length 2. That means that one can ignore the white vertices and you're left with a map. So throughout the talk, D will be a clean regular design, or equivalently, an orientably regular finite map. Now, there are certain operations which I've shown you already. I've shown you duality, and the point about duality is that it changes the generating triple. It almost transposes x and z, but the product has to be equal to 1. So you need to conjugate x by y to make the product of these generators equal to 1. The H2 that I introduced, this is one of Coxeter's what he called whole operations. And the idea is you replace the faces of the original map of design with new faces bounded by what he called J-holes. And these are closed paths which take the jth exit at each vertex. Imagine you're driving, you meet a roundabout, rather than taking the first exit, you take the jth exit each time, where J is co-prime to the valency. This means that you get a new permutation of the same order. So what you're doing is you're replacing the generating triple XYZ with X to the J, the same Y, and then the third ingredient has to be the inverse of the product of the first two. So for instance, H minus 1 is simply the mirror image operation. So a design is reflexible if and only if it's invariant under H minus 1. If Q is the valency, then these operations depend only on the residue class modulo Q. And moreover, they're multiplicative in the parameters J and K. So what you're getting is an action of the group of units mod Q. But remember, you can apply these operations only when J is co-prime to the vertex valency. Here's an example. This is Klein's map, the famous Hauptfigur of Klein, as a map of type 3-7. So triangular faces, 7 valent vertices, equivalently a regular design. And a 3-hole here is highlighted in red. If you start at 16, follow the edge to 5 and take the third exit on the right, you get this edge. Do it again here, take the third exit, you get this edge. You now meet the edge of the map and that reappears over here and you follow this red edge here. Again, you're at an edge of the map, so you reappear here. And in fact, what you've got is a path of length 4. When you apply the operation H3, you replace the triangular faces with foregons following these red paths here. So you get a new map out of Klein's map by doing this operation. So in general, if you're given a finite group G, you take the set of all isomorphism classes of these clean regular design with that automorphism group. You make these the vertex set of a graph, and then you draw edges to represent the actions of duality and these whole operations. They preserve regularity, they preserve automorphism groups, so they connect up vertices of this graph. And I'm going to use broken undirected edges for duality, these dashed edges, and directed edges for the whole operations HJ, except when they induce 2 cycles, then I don't need directions. So here's an example. This is the one we had before, where the group is A5, you have the dodecahedron, icosahedron, and great dodecahedron. the notation up here is the Coxeter symbol for the polyhedron. So valencies of faces and then vertices. And I've also put the genus where it is non-zero. So the great dodecahedron has genus 4. So that's one simple example of one of these graphs. Here are a few more for some very familiar small groups like A4 dihedral groups, S4, where you have, here you have the cube and the octahedron. A more interesting example is S5, where you get away from maps on the sphere. So here you have 7 possible regular dessins. They range in valency from 4 to 11. Here are their types, and underneath I've written their identifiers in Marston Conder's online list of orientable regular maps. And notice we're getting 3 connected components here. So there are 3 essentially different types of design with automorphism group S5, and you cannot convert one type into another. There's something special about this design. For example, it's not related in any obvious way to the other design, even though it has the same automorphism group. Well, we looked at for some good examples, and the obvious groups to look at first time were Hurwitz groups. So these are the groups which maximize the upper bound of 84G-1 for the number of automorphisms. They're the finite quotients of this triangle group, or equivalently, they're finite groups with generators satisfying these relations. And this means that they arise as automorphism groups of regular design of this type. And in 1969, Murray Macbeth characterized the PSL2 groups which arise. This is a very nice number theoretic description of the prime powers Q which can arise. So as an example, the smallest Hurwitz group is this group PSL27 of order 168, acting on Klein's quartic curve, this very famous example. And if you draw the graph of this group, well, here's Klein's curve here, genus 3, type 37. The directed edges represent H2, the squaring operation, and they generate a 3 cycle. Genus 19, and then 10, and then back to K, and then duality gives you 2 more. So there are 5 regular designs associated with this group, and they're related in this particular way. The next Hurwitz group is PSL28. This is the Fricker-Macbeth example. It was discovered by Fricker in the 1890s and then forgotten about, and then Macbeth rediscovered it in the 1950s. It has genus 7. So again, you've got a regular design here. And if you start here with the curve of genus 7, you have a much more complicated picture now. There are 14 different clean regular designs you can obtain by starting with this particular one here. And well, this is the picture you get. And you see the genus increases really quite spectacularly. You have maps of genus 71 appearing just by applying a few operations, duality and the squaring operation H2. Well, in general, then, what are we looking for? Given any 2 generator group G, finite group G, we'd like to know the order and the number of connected components of this graph. The order can be computed using the Frobenius formula that Nikolai told us about earlier, together with Möbius inversion inside the lattice of subgroups of G. So I won't say any more about that, but I will say a little bit about the number of connected components, because this is telling us how many essentially different regular designs there are arising from this particular group. So we have a few theorems. I won't attempt to prove them. But if you take the affine general linear groups over fields of characteristic 2, you can actually write down the number of vertices. Here, this is Euler's totient function, and the graph is connected. In fact, it's a very simple graph which you can draw for any value of E. So there's just one connected component. But by contrast, if you take the symmetric group, then there are at least the integer part of n over 2 connected components. One could make an estimate for the number of connected components, but we don't have an exact formula. And well, the basic outline of the proof is that you look at the involutions y in the generating triples, and they are up to automorphisms invariant under D and Hj. So by choosing these involutions with different cycle structures, you get different connected components. And this is the number of possible different cycle structures you can have. So here, the number of components grows, at least linearly. If you look at Hurwitz groups, well, symmetric groups are not Hurwitz groups, but alternating groups are, with just finitely many exceptions. This is a theorem of Nost and Conda. And by adapting his proof of this, of his theorem, one can show a number of components containing Hurwitz groups. That's H of G. It's the number of connected components containing a Hurwitz design. That also grows to infinity. In fact, it grows at least linearly again. So those are the main results. I'll finish with a couple of problems because like George and Nikolai, I want to see this continuing into the future. So an obvious question is look at the PSL groups for Q greater than 8, not just the examples we looked at. And even at 13, it becomes quite interesting. You have 33 clean dessins there. There are 3 Hurwitz dessins, but they're not all in the same component of the graph. And the reason is that when you look at the full automorphism group, including orientation reversing elements, 2 of them have PGL213 and 1 has PSL213 cross C2. And this prevents them from being in the same component. Another obvious question, how does the absolute Galois group act on this graph? It permutes the vertices, but not necessarily the edges. It permutes the duality edges, but not the edges representing the whole operations. So there's something rather mysterious here. And for example, in this PSL213 case, you have these 3 Hurwitz dessins. They're conjugate under the absolute Galois group, but they're in different components. So there's something a bit strange going on there. As I said at the beginning, we'd like eventually to generalize this to include regular design of all types, not just clean design. But there's a difficulty here. If you think of clean design as being finite, as coming from finite quotients of this free product, then the outer automorphism group of this group gamma, it's a Klein 4 group, and it has a natural action on design, namely generated by duality and the mirror image operation. If you go to all design, then you should look at finite quotients of this free group of rank 2. And now the outer automorphism group is an infinite group. In fact, it's isomorphic to the general linear group GL2Z. So you have a much richer supply of operations to consider than in this finite case where you have these basic 4 operations plus the other whole operations where the valency permits. Here, even without considering the valencies, you have an infinite group of operations there. So there's plenty more to be done. And I'll finish there. I've just put a few references up there if you want to explore further in this. So thank you very much for listening.
Thank you for sharing us these wonderful stories. Any questions for Gareth?
I have a couple of questions. First of all, when you start with some group, take generators and you transform them into powers, it's possible that the powers will generate a different group, a subgroup, right?
If the power J is co-prime to the valency, then you generate the same group. But if it is not co-prime to the valency, you could generate a proper subgroup. So in that case, you would obtain a disjoint union of isomorphic dessins. And we've avoided that situation by restricting to the case where J is co-prime to the valency. But one can certainly consider this non-invertible operation where J and Q are not co-prime.
In your pictures, it was always invertible, right?
Yes, always invertible, yes.
You also mentioned that in the case of PSL2 of 13, one of the Zens has full automorphism group. You meant orientation reversing automorphism, right?
Yes, all three of them have orientation reversing automorphisms, but the full automorphism group is not isomorphic in each case. In one case, there is an inner automorphism which achieves this, and in the other cases, in the other two cases, it is an outer automorphism, giving you PGL 213 as the full automorphism.
That your operations preserve full automorphism group.
They preserve the orientation preserving automorphism group, but like the absolute Galois group, they do not preserve the full automorphism group. You see, these three.
So it was not a proof that they go into different orbits, different components.
Yes, two of the dessins are in one component, and the third dessin is in the other component.
But full automorphism group doesn't explain this.
What we're looking for is invariants, which will tell us that certain dessins are in different components. Now, one possibility is the cycle structure of the involution Y. If dessins have different involutions Y, they must be in different components. Another invariant is the full automorphism group, and that's an example here. All of these dessins have the same orientation preserving automorphism group, but they can have different orientation reversing automorphisms.
Okay, thank you very much. Very interesting.
Okay.
Thank you.
Any other questions, Gareth? Gareth, can you please show your perhaps problem 2 with Galois group? Yes.
This one?
This question 2, yes. This is
yes.
What I was going to ask you about. So you have, what do you know about the statement of the question mark? Is it your guess or a result of experiments, or can you prove something about that?
We do not have much information. We should really follow Nikolai's example and do much more experimentation. I think that is our next project, to use GAP or magma or something to get more and more evidence. The examples I've shown you were all worked out by hand, but once you have a graph with 33 vertices or more than that, it becomes very time consuming and you can make a lot of mistakes. So really what we should do is bring in a computer and get a lot more evidence to see what is happening. We know that the absolute Galois group acts nicely on certain things like the duality edges, but we know that the edges corresponding to these whole operations are not respected in general by the absolute Galois group, even though they look rather like Galois automorphisms of cyclotomic fields. They behave very much like the Galois group of the Q cyclotomic field, where Q is the vertex valency, but they don't seem to behave quite in the way one would like. So they certainly destroy the graph. They permute the vertices, they permute some of the edges, but not all of them. And we need more experiments, I think, to see what's happening there.
Okay, thank you very much. I have a small remark about that, because exactly the same statement and on the same experimental level holds for the net of freed curves in the moduli spaces. The components of these curves intersect in the Belyi pairs, and in the small number of cases that I'm able to compute, exactly the same statement holds. Some years ago, I have asked Mike Reed whether he could explain it theoretically. And it is important that Mike answered yes and gave a reference to some of his old paper. Unfortunately, I was unable. Up to now, I was unable to understand it. Maybe I should try harder.
Well, that's very interesting, thank you. But if you find it hard to understand, I will find it impossible. I look to you for guidance on this. Thank you, George.
Any other questions or remarks?
Actually, I have a question. Could you please let me know if there is reasonable to discuss about maximal number of connected components if we take fixed amount of edges or maybe some bounded amount of edges?
Oh, that's a good question. We haven't really thought about that. You would need a group with a lot of involutions in it. Probably yes. Symmetric groups are a good place to look, but proving that you have an upper bound, I think, would be rather difficult. Yes, that's something to think about.
Thank you.
Okay. Any other questions or remarks? Well, then thank the speaker again. Now we have a 20 minutes break and hope to resume at 2 o'clock Moscow time with Gareth chairing the next section. Okay.
So if we consider these two pictures, here on the first picture, we have a simple assembly graph. And on the second picture, this is assembly graph, but this is not simple. Surely, for any simple assembly graph, we have just two vertices of valency 1, or actually it can be closed. We can do something like this. And it will not have vertices of the valency 1 at all. So we have this just two possibilities. Okay, it's an easy observation that if we have a simple assembly graph, then it contains exactly this number of edges. And it's not directly, but we will see this in few minutes and few slides, that that simple assembly graphs are exactly the same that double occurrence words, and so the thing which we need for our original genetics problem. Sorry, we can see, I am sorry. So these are two observations by Natasha Janoska from Florida. The first is about the number of ages, and the other one is that equivalence classes of double occurrence words are in bijection with the isomorphism classes of simple assembly graphs. And so the simple assembly graphs are the thing which is used in the modeling of genetic rearrangements. Now one can just for fun check that these two words are indeed not in the same equivalence classes, since the corresponding graphs are not in the same isomorphism class. Now we consider quite another type of path in our graphs. The first class of transversal path was needed just to be within the frame of our model, of the model which describes the genetic rearrangements. And then to work mathematically with this model, we need the path where all vertices are distinct and all consequent edges are neighbors in their common vertices. Such paths are called polygonal. Now, two paths are disjoint if they have no common vertices. Of course, as a consequence, they have no common edges as well. And we want to consider polygonal disjoint paths which cover all vertices of a given simple assembly graph. Not we want, but the people consider these coverings. The set of pairwise disjoint polygonal paths is called Hamiltonian if the union of these paths covers all valency 4 vertices. Again, we just forget about valency 1 vertices. So the simplest example of polygonal of Hamiltonian sets is just the set of all vertices of our graphs. Each vertex by itself is a polygonal path of 0 length, and so we always have such a covering. But we want to have covering with the minimal number of pieces. We want this again because of these genetic motivations. We want to have the minimal number of these additional templates. So an assembly number of a graph is this minimal number of polygonal passes, which is necessary to cover all vertices of valency 4. For example, if we consider this graph, then we can take this Hamiltonian set of polygonal paths, the one long path and two paths of the length 1. And actually, this is the minimal set for this particular graph, but we will not stop on the proof here now because of, okay, here it's just some combinatorial reasonings, but in general, it's always not so easy to find if, okay, actually as usual in such questions. the graph for which there is just one polygonal path is called realizable, and the other graphs are called unrealizable. And actually, the graph can be of rather difficult structure, but realizable. And the following notion is the minimal realization number. So for any number n, we would like to consider the minimal graph such that the assembly number of this graph is n, minimal in the sense of the number of valence of vertices. Sorry. Okay. Yes, of valency 4. And if we have a graph, there is also a theorem by Janoschka and her co-authors that for any simple assembly graph with n vertices of valency 4, the set, we consider all sets of Hamiltonian polygonal pairs of this graph, all such coverings, and their number is just not greater than the 2n plus 1 Fibonacci number minus 1. So, for example, if we consider this very simple graph, then we have just one covering, just empty actually. And if we have this graph, then we have these two coverings and also trivial covering. So there are 3 of them. And now we would like to consider some particular graph. It's called a tangle court just because of it looks like this telephone, this very old-fashioned telephone cord. This is this graph. Okay, here vertices are which. Here the vertices are the intersection points, and it can be seen how the edges intersect, which is on the top and which is on the bottom. This graph corresponds to the following assembly word. This graph is defined inductively. And by definition, the TCN is obtained from TC sub n minus 1 by replacing the last n minus 1 by this sequence. So from this word, we obtain that word. This is a very important example of it's important in many problems of this study. At first, it has a very, very big amount of distinct Hamiltonian polygonal paths, just this one. And it can be easily seen from this theorem that the upper bound, which I mentioned, is achieved on this graph. And actually, there is a conjecture that it is achieved only on this graph and no other graphs where it can be achieved. The conjecture holds true for n is 1, 2, 3. Actually, we worked on it and we have some ideas how to work, but this is not finished. Just what we did is that the minimal number of edges on which we need to add loops in order to obtain graph with the bigger assembly number is 3. Okay, maybe, no, okay. The problem is that it's easy to find examples of graphs with assembly number 1. There are some specific construction how to increase assembly number. For example, if we add a loop to any edge of a graph, we definitely increase the assembly number. However, we increase the number of edges much more than the assembly number. And this is the problem. Okay, I think I have some time constraints, so I miss a little bit. Just composition. So it's a separate problem how to increase the assembly number of a graph. We have graphs with known assembly number, how to construct something from them. The main thing is the composition. We just adjunct 2 graphs by the vertices of valency 1, and it's easy to see that we get again a simple assembly graph. Assembly number can be changed like this, can be either sum of or sum minus 1 in this case. And we say that graph is additive if there is the sum. So we find different ways how to find the additive graphs. And okay, this is also the way how to find additive graph, just to take composition with some specific graphs of some special structure. And now I want to say a few words about another problem. This is the problem of genus range for assembly graph. Namely, if we have an assembly graph, then it can be converted to a descending fan on different surfaces. And what the possible genuses of these surfaces? This is the question. So these are just some computations for different small n. And actually it is proven recently by Bach and Bach, Janoschka, and the others that for any m there is an integer n such that m is such that all numbers from 0 to m is a genus range of some graph with n 4 valency 4 vertices. For the tangle chord, it was proved that there are such genus ranges. And there is a conjecture that the only graphs such that the genus range consists of 0 and 1 are obtained from this word by the adding of loops. But more interesting actually conjecture that the maximum genus range of any assembly graphs with even number of valency 4 vertices is like this for any integer. So actually that's all. Thank you very much. This is just several pictures for the questions. Thank you.
I think we have time for a couple of questions or comments. So thank you, Elena. Are there any comments or questions?
I probably misunderstood. Is the valency the same as the degree of vertex? Or maybe I misunderstood.
The valency is the degree of the vertex, yes, as usually. Sorry for not pointing out.
I have a somewhat abstract question. So the nature provides you, the group of authors, with graphs and with some coding. And then you consider their embeddings in surfaces. Do these surfaces have any meaning in nature, in the biology?
I think no. I think the surfaces does not have any meaning in biology. At least nobody found this meaning at the moment. However, surfaces appear naturally from the fixed order of edges in the vertex, and the order is fixed by the original biology problem. So probably this is just the question of time when we can find this explanation of what I do not think actually that surface as it is can play some important role, but maybe the genus can play some role, and it's an interesting question.
Do we have any more comments or questions for Elena? Well, let us thank Elena again for a very interesting talk. Thank you, Elena. So I think we're due to start with Vladimir Gurvich.
So I'm starting. This is the title and authors. So I even have two from Slovenia and Andrei Boros from Rutgers. Okay, so that should I repeat the title? Degree sequences of dual graphs on surfaces. So first, let me start. What is a map? Map on the surface. We consider embedding or drawing of a graph on the surface S, and we require the following. Vertices are mapped to distinct points, which is natural. Edges are drawn as arbitrary curves connecting the images of the endpoints, and they cannot intersect except on the ends. Now, if we cut the surface along these lines, these curves, so in other words, we subtract the graph from the surface, it will be split into connected components, and we require that each component must be an open disk. Otherwise, it's not a map. In particular, this condition implies that graph must be connected. But graph may have loops and multiple edges. Now, what is the dual? We have to introduce a graph dual to G. It realizes neighborhood relations among the countries of G. These connected components are called countries. Two countries are neighbors if they have a common edge. Common vertex would not be enough, common edge. If there are several common edges, then G star dual graph has multiple edges between the corresponding two vertices, two countries. A country may also have interior edge which belongs only to this country. Typically, edge belongs to two countries which are neighbors, but it may be interior because on the surface, vertices and edges can be merged, glued. So in this case, this edge is a loop. Such edges are loops in dual graph. So by this constructions, graph two graphs G and G star have the same set of edges. More precisely, there is a one-to-one correspondence. We fix a one-to-one correspondence between their edges. So vertices and edges and countries and the same edges. These are two dual graphs. A pair of graphs such that their edges, they have the same set of edges, we will call it a plan. Sometimes people call it passport. So that's two graphs, vertices and countries and edges are the same. A plan is called geographic if it is assigned to a map, if it can be generated in this way. And the question, which plans are geographic? This is not yet main question. This is a preliminary question. Which plans are geographic? And it was resolved long ago. It was resolved in '65 by Jack Edmonds. But it's published in this Journal of National Bureau of Standards of America. Between Rand and Princeton, Edmonds works in National Bureau of Standards, and several remarkable his papers on matroids and topology published in the corresponding journal. So was not very popular. Now it's more popular because of Edmonds' works mostly. He gave a proof which is constructed, and it allows to generate all maps assigned to a given plan. And if no, then we say no plans. And it's not geographic. No maps in plan is not geographic. Then we did not read. We rediscovered with Shabat this result 24 years later. And we published in Soviet Math Teklade. I met Edmonds in 2009 in Paris 6. We shared an office for 3 months, and that's how I learned about the paper. And he learned about ours. I thought he might be angry that for republishing his result in 24 years, but in contrast, he was happy that somebody thinks about the same things. And we Googled both papers and learned that he had 7 citations and we have 4 citations. Not many for 44 and 20 years, but now it's more. Now Edmonds' paper, it becomes more popular than probably 50 citations. What is Edmonds' criteria? So how he characterized geographic plans? It's direct generalization of famous Euler's theorem about Königsberg bridges. So graph is Eulerian if it admits Eulerian tour, which passes every edge exactly once, and it starts and begins in the same points, and the theorem by Euler that such graph must be connected and every degree must be even, and both conditions are obviously necessary because connectedness is obvious, and it should be even because if you came to a vertex, you must be able to go out. So then, okay, why they are sufficient? Because you partition graph into some number of Eulerian tours, because evenness you can do this, but you must be able to reduce this number to 1, only 1 tour, and this is easy to do because if two tours share a vertex, it looks like digit 8 or symbol infinity. Then you have 2 cycles and you can make it 1 cycle, one tour. Moreover, you can make it in 2 different ways. And this is what was not important for Euler, but it's very important for Edmonds that you can do it in 2 ways. So how to generalize this to surfaces? Given a plan, so you have graph G, vertex edges, and G star, countries edges. Fix an arbitrary pair, vertex country, and count the number of edges incident to both V and F. And this number must be even. Note that H is counted twice when it is a loop in G or in G star. and 4 times if in both. So such edges respect evenness automatically, and we can be ignored. We can restrict ourselves by edges which are simple in both G and G star, and their number must be even. This is evenness condition. It can be reformulated elegantly in as follows. We consider incidence matrix of G and incidence matrix of G star. They have size m, n times L and m times L. So if we transpose the second matrix, we can multiply. Matrix product is well defined, and all n times m entries of the product must be even. So this is evenness condition. Also, there is connectivity condition, but look, I don't want to repeat all this. So there are m plus n connectivity conditions. I will, if I will have time, I will return to it, but actually, let me skip it now. By the way, in fact, it was my talk 5 years ago when Shabat was 65. So I'm sure you remember it. And let us focus on today's topic. Today we focus on the degree sequence of G and G star. Degree sequence. This Edmonds criterion can be applied to characterize degree sequences of G and G star. Characterizing these degree sequences of planar graph, by the way, it's like not related, but similar problem. It's challenging problem. And we consider the problem characterizing degree sequences of geographic planes. And this is also difficult. A variant of this problem, if we restrict ourselves, many people restrict themselves by orientable surfaces. So, but we don't. Moreover, we cannot distinguish orientable and non-orientable surfaces. I will talk about it. So the latter problem generalizes problem studied by Eberhard in 13 decades ago. So that's old. That's he considered only convex poleda. So in other words, geographic plans arising from planar tree-connected cubic graphs and their duals. And there are many. He started, and there are like about 15 or 20 papers on this subject. But it's about polytopes. So again, let us return to our problem. G star is geographic plan. L, the number of edges in each of two graphs. Then degrees of G, d1, dn. This is degrees of vertices of G. And T1, Tm, degrees of vertices of dual graph. And then it's just simple arithmetics that sum of coordinates of these two vectors are equal, and they are equal to 2L. And then L is the number of edges. And then high Euler characteristic of the surface, it can be embedded or not, is the Euler, but if it can be embedded, then high is equal to this. And L, we know, L we can compute, yeah? L we can compute by this formula. And N and M are just dimensions of this degree vectors. Okay, which sequences D and T satisfying this condition still cannot be realized, so that's as degree sequences. So this is like, let's say, feasible if they satisfy arithmetical condition, and let's call geographic B vector dt called geographic if it can be realized by a geographic plan, and it's not always possible. But when it's possible, we make use of Edmonds criterion because it's natural thing. We can say when it's plan or when a plan is geographic or not, and we can, given degree sequences, we can consider all feasible plans. So, and there are exceptions. It may be feasible but not geographic. And these exceptions we found by computer. Yerney wrote a code, which is actually that's polynomial procedure and code efficient. We just consider all geographic planes and we generate the corresponding degree sequences and we see which one are missing. And we can do it up to 9 edges. With 10 edges, it's already a problem. But 9 is big enough number because we can guess some infinite series. And we found such series for sphere, χ equals 2, and projective plane, χ equals 1. But if χ is non-positive, in this case, we didn't find any exception. So we conjecture that there are no exceptions if χ is not positive number. It is known, however, now that's what is orientable or not orientable, that if χ equals 0, exceptions exist for torus as well for a Klein bottle. It's very strange that they exist for the torus, sorry, for Klein bottle, but I'll give you example, but not for both simultaneously, not for both. You understand? There are plans which cannot be realized on torus, which is natural, but we know even a plan which cannot be realized on Klein bottle only on torus, which is strange because most likely if you glue polygons with high probability, you get a non-orientable surface rather than orientable. But I'll show you the example. And but not for both simultaneously, not for both simultaneously. In general, our method has the following disadvantage, or it can be viewed as an advantage, I don't know. It does not distinguish orientable and non-orientable surfaces. Given a feasible B vector, we compute χ, apply the method, and get answer, yes or no. Answer no means that dt is not geographic, and no surface will help. Answer yes means that it is geographic, but still we do not know on which surfaces it can be realized, and our method doesn't tell it. If χ is odd or χ equals 2, there is no problem because only one surface exists. However, if χ is not positive and even, then there are two possible surfaces, one orientable, one non-orientable, and we cannot distinguish. We cannot distinguish. Our geographic plan could be realized in one of them or on both. To decide which case takes place, we would need some extra analysis, which is much more complicated than our method. So a geographic plan which can be realized on the torus, but not on the Klein bottle. It is known that torus is 7 colorable. So-called Hurwitz graph can be embedded in the torus and partition it into 7 hexagons, such that each two have a common edge. You understand? 7 hexagon, each hexagon borders with 6 others. So every 2 have a common edge. Thus, it requires 7 colors, but our subject is different. So this Hurwitz graph has 14 vertices and of degree 3, each 21 edges. So 14 vertices, each one of degree 3, and it has 21 edges. So vector D is 3 to 14, 3, 3, 3, 14 times. And vector T is K7, G star is K7, so it's 6, 6, 6, 7 times. So this is degree sequence. This is a plan, yeah, 3 to 14 and 6 to 7. If you multiply 6 to 7 is 42 and 3 to times 14 is 42, and number of edges is 42 over 2 is 21. So M is 14, N is 7, L is 21. So M plus N minus L is 0. So it can be realized on torus or on Klein bottle, and it can on torus it's classical example, but it can be proved that on Klein bottle it cannot be realized. That we use Fano plane, it's a new proof. We use Fano plane to prove it not realizable on Klein bottle. So again, the summary: there are exceptions for torus, there are exceptions for Klein bottle, but not to both. It's conjecture. We did not prove it. But when can we prove it? We can prove it when degrees are high. If all degrees are 10, then it's not difficult to prove. If all degrees are 8, also it's possible to prove, but it's already very long proof. But it's still very weak results because the computer shows that they do not exist for no degrees. For any degrees, they fail to exist. Okay, now a generalization. Three-colored triangulations of surfaces. Instead of dual maps, we consider three-colored triangulations of surfaces. This is a more general, surprisingly, this is a more general object that consider a surface an arbitrary map M on it, generating by embedding of graph. If in each country, let us fix a point f prime, which is called capital, and in every edge, let us fix a point e prime. We'll call it checkpoint or custom, and then the set of every capital we connect to every capital we connect to every custom and every vertex of this country. Look, this, let me skip this. This was introduced by Shabat and Voevodsky in paper 1990, and maybe it was known by Grothendieck in 84, but this paper was published in 97. So this just, I want to show you this example. You see, this is a country, this is the capital, and we connect it to every vertex, every corner, and we connect it to every checkpoint. And this country is triangulated. And pay attention that each triangle has, there are 3 types of vertices: capitals, vertices, and checkpoints. And each triangle contains all 3 types, 1 to 3. And also there are 3 types of edges. And we can color 3, so this is, every country is triangulated, so the whole surface is triangulated. And each, by construction, this triangulation is tricolorable. Not every triangulation is tricolorable. So, and also this capital, it contains only edges, one type of 1, 2, 1, 2, 1, 2, and they alternate. So that must be even. Every three-colored triangulation must be even. So degree of every vertex is even. But pay attention, what is the degree of checkpoint? Degree of checkpoint, a checkpoint is always 4. Degree of a checkpoint is always 4. So this is what is special in it. We can waive this condition and get more general object. So that may appear in 84 in preprint by Grothendieck and published in 97. So we can extend our problem to this. Instead of maps, we can pair of dual maps, we can consider three-color triangulations and ask the same questions. And actually, algorithm works. We can check triangulation is geographic or not. First of all, we have to, withdraw the last sentence. We have to introduce degree yet. Hence, each vertex of T, a triangulation has an even degree. So because they are even, let us divide them by 2 and consider 3 vectors. D, T, and this delta. And sum of delta corresponds to checkpoints, D corresponds to capitals, T corresponds to vertices, or vice versa. So sum is equal, all 3 sums are equal to 2L. This I consider triangulations obtained from maps. And Shabat noticed that one can waive the set of conditions that this delta, all coordinates are 2. So we have 3 vectors, and the last one is 2, 2, 2, 2. And instead, we say that we consider any triangulations, not necessarily with checkpoints. So there are three vectors, d prime, t prime, and delta, and they have some degrees, and sum of degrees are equal. these three sums are equal, denoted by S, the sum, then Euler characteristic of the surface can be is number of vertices n plus m plus k, because there are three types of vertices: n vertices, m capitals, and k checkpoints, but not checkpoints, k of the third type, minus 3s plus 2s. So this is number of edges, number of countries. So that's n plus m plus k minus s. And the same question, which this is feasibility condition, which are realizable by which are geographic. And actually this is I don't know, because of this COVID, this research stopped for a while, but Yerney has to write the code. We have an algorithm. He should write the similar code and just check it, and if we have data, we can try to prove something. So probably I can guess that exceptions still exist. Of course, they exist for projective plane and for sphere, but maybe they already exist for torus, because this is more powerful set. Yeah, you understand. There are more these triangulations than maps. So there may be more exceptions, but I would guess that they finish if high is large enough, they would disappear. So, okay. And again, this is not ready. These are all projects, but what is ready is the case is 2, 2, 2, 2. Delta is 2, 2, 2, 2. But what does it mean ready? We have some conjecture and we have some very partial results. Okay. Then do I have more time? How much time do I have?
It would be nice to see whether Gareth hears you.
Sorry?
Whether Gareth hears you. Gareth is...
You... So if I have 5 minutes, I would go to this Edmonds criterion. If not, then I would finish.
So perhaps there is something technical, and then yes, you have 4 minutes. Oh, here's Gareth.
Sorry? 4 minutes? Okay. I don't know. Maybe then. Okay, then Edmonds criterion. Then maybe I finish. Maybe you have questions. So, congratulations.
Thank you very much, Vladimir. Thank you. So we have time for a few comments or questions.
When we multiply two incidence matrices, do we mean the Boolean semirin or the field F2?
Just evenness, look, that's incidence matrix. One matrix is M times L, other matrix is N times L, because common set of edges, yeah? So you transpose the second matrix, then you can multiply. Each row is either 1, 1, it's incidence matrix of a graph. So every row is 1, 1, the rest are zeros. Or if it's a loop, then 2, the rest are zeros. So you just multiply scalar product row by column. Then if you have entry 2, then it's automatically even. You only care about evenness, so it doesn't matter. You can multiply modulo 2. But if you have edge which is simple in both, then its contribution is 1, and number of such edges must be even. This is necessary for plan to be geographic. If it's 2, then 1 times 2 is already even, and 2 times 2 is 4 also even. And H may be double loop, yeah? Consider projective plane and basic loop in the projective plane. Then it's loop in G, and it's also loop in G star. or H may be loop in one graph and simple H in another graph, but we care only of edges which are simple in both graphs, and the number is even. This is evenness condition, and also there are also there are connectivity conditions, n plus m connectivity conditions, of which I did not have time to talk. But I can say, if I have 1 minute, imagine you have a country. Then this country on the surface, it generalized. We can associate to this country an Eulerian tour on the primal graph. Just go along the perimeter of this country inside the surface. Then this is what you have. You have alternation, H vertex, H vertex, H vertex. How many times? Every vertex can appear several times because they can be merged, they can be glued. Yeah, the country is a polygon and its vertices are glued, but each H appears once or twice, not more than twice. And when it appears twice, when it is inner H of this country, then it's only border this country. So this is Eulerian tour and primal graph. And similarly, every vertex generates an Eulerian tour in dual graph. And all these graphs, m plus n, must be Eulerian. Evenness condition is summarized by this product of matrix evenness. And connectivity condition is separate for each vertex and for each country. Okay.
Okay, thank you very much, Vladimir. I think it's nearly time for Natalia's talk now. So let's thank Vladimir again for a very nice talk. Our next speaker is Natalia Amburg. Natalia, are you there and are you ready to talk?
I want to say about simplest construction. Georgy Borisovich, maybe with Voronov and other people proposed for our seminars generalize our construction, dessins d'enfant, to dimension more than 2. I want to do one step, and our object be 3 dimension. Okay, it's well known that partition function for matrix model count of dessins d'enfant. We start off integral over matrix vector space, and we integral with Gaussian measure. And this place for a function over this vector space, and we can calculate this integral, and this integral count dessins d'enfant. And we take tensor model. We have
is there any measure to integrate to be written? Yes, something like this.
Okay. These are 3-dimensional object. We have 3 vector space, 3 different vector space, and we have a tensor of these vector spaces. Polylinear function on this, and this. Okay, this is a vector space, and we want to integral over this space. Okay. We want to Gaussian measure integral we have this and dual space of this tensor and in this we contraction this and this tensor together, and we have number and this our Gaussian measure. Okay, this is the simplest Gaussian measure on this vector space. Okay, and this place for function on this place, and we denote by operator, and it's a well, okay. This is a multiply of these tensors and contraction together. Okay. We want to integral this multiplication. And if we want to, this integral is not equal to 0, we need a pairing our tensors and dual tensors together. And for Wick theorem, and we need the first contraction, the first contraction the tensor together for equal to numbers, and when we have integrals, we okay. We need pairing this tensor together for two steps. Okay. I want to picture for this construction. Okay, this tensor I draw like black vertices. If I have n tensors, I have n vertices. This tensor I draw like white vertices. And our all contraction, our indices are permutation of this black and white vertices. We have free color for contraction, first number, first indices, second indices, and third indices. Okay. And third, for example, and we have order for contraction our indices. First for first, second, first for second, first for second, and down. Okay. If we want to integrals, we need next permutation and fourth color. Okay. This construction I want to see like three-dimensional object. Okay. Let's start to three-dimensional sphere. We have two parts of this manifold. This is a disk of dimensional of three. This and this. And boundary of this part is a sphere dimensional 2. Okay. Let us see on this sphere like tetrahedron. And this and this like inside tetrahedral and outside tetrahedron. Let us color this tetrahedron by 4 colors. We have 4 sides and coloring these 4 colors. Okay, and these permutations is order of gluing together this tetrahedron. our sphere consists of two tetrahedron, like up is white and down is black, and glue together black and white tetrahedron by side same color, like in these permutations. And we have three-dimensional object with boundary. What is boundary? Boundary is a generalized descendant form, free coloring, or disjoint union of symbols descendant form, free coloring. And if we have integral, we glue together red, all blue, and all green side, and we see only 4 color, but different 4 color. 4 color and white inside tetrahedron, and 4 color with black inside tetrahedron. And we have triangulation of these surfaces. We have surfaces, only 4 color surfaces by boundary this object. And we have black and white triangles, and boundary of triangles have 3 coloring and glue together, and we have descendant form 3 coloring. Okay, if we have these integrals, we glue together our triangles boundary of our objects, and we have 3-dimensional manifold without boundary. I think that's all. Это слышно, что я способна сегодня.
Thank you very much, Natalia. Are there any questions or comments for Natalia, please?
It was not quite clear. You start with 3 colors from tensors.
Yes.
So you have you got 3 permutations.
Yes.
And then you come to tetrahedrons. There are 4.
Yes. We have 3 count for write this function, but for integrable, for integration, we need 4 permutation and 4 colors.
So what is it for? The product of?
No, we have this, and we need 4 color. With theorem, for this measure, we have weak theorem, and this integral is multiplication of integral by pair, sum of multiplication by integral by pair, and we need 4 pairing. This pairing, this pairing, this pairing, and for weak theorem we need 4 pairing, and we have 4 permutation and 4 color. 3 color before integration and 4 color.
You sum of the fourth permutation.
So you start with writing some integral. So you are trying to count something, right?
Yes.
And but you didn't know from start what you are going to count.
Yes. It's obviously we this tensor model короче, изучают физики, и они ничего не знают про эти поверхности и про эти... Вообще, ну так обычно бывает. Они изучают что-то, но никто ни с чем не ассоциирует. А это более-менее конструкция, вот я придумала, что можно так на это смотреть.
Are there more questions for Natalia or more comments?
I have a question. The classification of three-dimensional manifolds is a terribly difficult problem. So if one enumerates three manifolds, one needs some characteristics according to which to enumerate them. And I don't see clearly what could be these characteristics. Even to recognize a sphere, a three sphere, was a very difficult result, published not very long ago.
Так, я половину не поняла, половину не услышала. Если кто-то мне поможет.
Sorry.
Okay. We have, okay, this construction counting the covering of sphere unramified without oscov of this tetrahedron. Inside tetrahedron is covering, outside tetrahedron is covering, and only edges and vertices we have unramified. This edges and vertices ramified ramification set of this covering, and we count this these objects.
This construction allows to get a surface, some surface inside the two-dimensional manifold, like George talked about here.
Yes, we have surfaces inside our manifold.
What is the surface? The complete pre-image of the
We
tetrahedron
have
surface, or...
several like object. We have triangulation. We have our three-dimensional manifold glue from tetrahedron, and we have triangulation. We can take these vertices and edges and glue.
You mean the same construction that George?
Yes, and these surfaces inside our manifold exist. But I say about another construction. We can glue only three colors, and we have boundary of this object is descendant fun, several descendant fun, and for integration this formula we need glue together black and white triangle of our construction of descendant fun. Thank you.
Are there any further questions for Natalia or any further comments? Well, let's thank Natalia and all the speakers, Vladimir and Elena, for some really interesting talks this afternoon. Thank you, all three of you.
Welcome everybody to this afternoon session. Our first speaker today is Boris Bychkov, and he will talk on double Hurwitz numbers, maps, topological recursion, and dualities. Please.
Yes, thank you, Sasha. So I'm very glad to speak on this conference to the occasion of George birthday. So I'm happy to congratulate. And I may say that I remember the previous time, the previous conference in the occasion of 65th birthday. As I remembered, also in Independent University of Moscow, but as I remembered, we had there one day, and this year we have 2 days, so we have a bit more time, and moreover, we with the next speaker, with Peter Dunin-Barkovsky, we use the opportunity, and we will speak on the one and the same topic. So I hope that will, because of we have time, we will be clear and so understandable. So please stop me and stop us if there are some questions. Okay, so I will speak about this double Hurwitz numbers, maps, topological recursion, and dualities. It's a quite big ongoing project with Petya, Maxim Kazaryan, and Sergei Shadrin. So this we have this 3 papers exists on archive, and at least one we're writing now. So maybe let's start. So yes. So what problem we were solving? Let me start with some example of object that were counting. So let gamma Gn is a set of maps. So what would you like? Embedded graphs, ribbon graphs. So we of genus G with n vertices and k1 etc. kn valences of vertices. And so we take this generating series for this for this quantity. So this WGN is the sum of overall graphs from this gamma Gn. This x1 and xn are just variables. As usual, we divide over automorphism group of G, and this this k1 sure here should be k1 dot etc. dot kn. It's just some factor that is convenient for us. So for today, for me, this WGN is the main object, and so what this story about? We are going to. So I would speak about some recursion on this WGN, on this quantities WGN, which calls topological recursion, and about some generalization of this recursion to the more general function like WGN. And this topological recursion is quite not very old procedure due to Chekhov ANR and RN10, but it turns out that it's very universal, and very many different enumerative problems fit into this recursive procedure. And for example, the maps or embedded graphs also is an example of this enumerative problem, and so that's why I started with them today. So what's this topological recursion is? So I will not give the definitions of topological recursion, and I will not write down the identities of the recursion. They are quite big and not very informative. But I will give a equivalent reformulation of this recursion. And so here it is on the slide. So what's the meaning of the recursion? The meaning is the following: that there exists in this WGN we have variables x1, etc., xn. So there exists a change of variables x of z such that this WGN becomes rational in this z coordinate. And in the case of enumeration of maps, this changing of variables is just x of z is equal to z over 1 plus z square. That is this change of variables. And yeah, so this means that this WGN is a global meromorphic function on the Cartesian degree n spectral curve. In this case, it's just the CP1. Sigma is a CP1, and in the theory of topological recursion, it's called spectral curve. And so the poles so we have a rational function in Z, and the poles of this rational function are predicted by this x of z. So it's just a critical points of this function x of z. So it's zeros of dx, and in this case, the poles of this WGN just are plus and minus 1. So this WGN is like some polynomial in Z over some product of Z plus minus 1. And so the also so-called loop equations, what we see, okay. Also loop equations, it's some statement about holomorphicity of some combinations of these functions WGN for different G and N. They means that they determine the principal part of poles of WGN as a rational function in the first coordinate. So recursion itself, it's a function of so it has some special coordinate z1, and all other coordinates are just parameters in the recursion. And by these conditions, so that we have a predicted poles and principal part of poles, and we know the principal part of poles, so we recovered these functions as functions on CP1 uniquely. And this is the meaning of for me now of topological recursion. So without this huge identities of the recursion itself. So the identities itself, it's some quite big identities, including some calculation of residues or of some forms which are connected with this WGN functions, which I determined. Okay, so and next, how we treat this with this WGN to work with these conditions of topological recursion. So maybe I should say that it's a long story, and it's a very well known fact that this generating series for enumeration of maps problems or Hurwitz numbers problems, which I didn't mention yet, but they exist here. So this WGN series can be can be expressed in terms of some operators on the Fock space, which I'll define now. So it's very well known stuff, but we use it. So we saw on it on maybe on quite a different angle, and use this very well known stuff to prove the topological recursion in very general situation. So it just some informal words, but by now we have this example of enumeration of maps. So what is the Fock space? What is all this stuff about Fock space? So you may think about it just as a polynomial in Laurent polynomial in variables p1, p2, etc. So it's this curly f, but it's really a bosonic realization of a Fock space of there are famous boson-fermion correspondence, but we would not need it but by now. And what's useful because curly f space in the Lie algebra GL infinity. So not quite GL infinity, but the central extension of GL infinity, which I denoted by a hat symbol. And this is the Lie algebra of matrices with finitely many non-zero diagonals. And so it's spanned by this just identity matrices EIJ, where we have one on the intersection of I and J column and row, and it's indexed by half integers usually, and we have our commutation relations in this GL infinity, GL hat infinity, as here written down, and the useful of this viewing that the calculations of this. So we want to prove something about this WGN series, and some you maybe remember all these conditions. We want to prove something about the pools, some rationality statements and all this stuff. And instead of proving this on the language of some generating series in P coordinates, we prove it for these matrices in the representation, and it's much easier because of the relations in this representation of the Bosonic representation of the Fock space. And so how we express WGN in this formalism of operators in GL infinity. So let GM is this sum, so just EK minus MK, just matrices when one non-zero diagonal. So on this guys is GM. In terms of the operators on the Fock space, it just or multiplication by P minus M if M is less than 0, is this differential operator if M is greater than 0, and 0 if M is equal 0. So I forget to mention that this is a zero charge Fock space, if you know, but nevertheless. So and this this 0, the first 0 is a vacuum vector, so it's just a 1. The second 0 is a co-vacuum vector, sorry, so it's just in the language of generating series, it's taking the free term, taking a free term of the series, and one more operator. It's a diagonal operator, so it's a diagonal matrix with this W small k on the diagonal, where WK defined by this identity. And what I want to say here that this identity is important because of this identity holds for the case of maps. So now I want to emphasize that we are in the case of maps, and in the case of maps we have this identity for this W, and for other enumeration problems we'll have different this coefficient W case. Okay, and then we can write this series WGN as a vacuum expectation value. So no, it's more convenient not only one WGN, and let me collect the new series. So sum over G, and what is written in the right hand side. So here you see this xk to the power I, it just coordinates. This gi is you see not yes, it's maybe, yeah, great. This gi is these operators. This exponent of d is this exponent of this guy, and this e to the power g minus 2 is just g minus 2. It's this operator there where m is equal to minus 2 here. So and what's happened here? So so it's useful to calculate it in the language of matrices of representation of Fock space, but to think about it, it's more maybe so easier in the language of series and polynomials in p variables. So here we have some operators in p variables, and we act this operator acts on the one, on the identity, and then we take a free term of the result, and this and then we take a coefficients in front of h power to the power to g minus 2 plus n. Then we obtain this wgn, and then if we take a coefficient of x1 etc. xn to the appropriate powers, we get this this G, our maps that were on the first slide, and also this dot you see here, the white dot, it means that if we take just vacuum expectation value, just this thing without a dot, we will have a disconnected. It's a disconnected vacuum expectation value, and we obtain also a connected and disconnected embedded graphs. So to obtain, and I didn't mention, but I started with only with connected embedded graphs, and to obtain the connected ones, we have to use some inclusion-exclusion procedure to obtain connected guys on the left-hand side. And here, this dot means that I apply the inclusion-exclusion procedure to this disconnected vacuum expectation value. Okay, so this is the story for maps, and now what about generalization? So generalization, we called it, so it's m endpoint functions. So instead of taking, so we had function w with one tuple of parameters x1 etc. xm, and now we have two tuples x1 etc. xm and y1 etc. yn, and this omega mn g again. So in the left hand side some generating series, and I will explain what count this generating series. And in the left hand side we have this big vacuum expectation value. So we had, for the case of maps, just we had this guy, and now we let me consider this guy. So here again, these j operators and these x variables and these y variables and this j minus I operators, and also these parameters ti here, new parameters ti and si, with again with j I and j minus I guys. So this x and y again variables, and these t's and s are infinitely many parameters. So what all this mean? So what we count here? We count the following. So we count so-called hypermaps. So it's bipartite embedded graphs with some conditions. So bipartite embedded graphs, I mean that we have black and white vertices, and you may think about so I think about maps as a bipartite graph which has bipartite graph which has all for example white vertices of valency 2. So if you have a just embedded graph, you can put white vertices on the center of each edge. So you obtain a bipartite graph with all white vertices having valences 2. And here hypermaps, for me now, it's when we allow any valences of white vertices. So here we have M black, and here new condition that we have marked vertices and unmarked vertices. So we have M black marked vertices, which is valences of which valences are the exponents of x variables, as was on the first slide, and any number of unmarked black vertices, and the valences of these unmarked black vertices are indexes of T. So the Ti means that, so the monom of T's counts these unmarked vertices, and Ti means that we have a black vertex of valency I. So and also we have white vertices and marked, also marked and unmarked, and marked white vertices accounted by the exponents of y variables. And again, we have an arbitrary number of unmarked white vertices. It's counted by a monomial of these s variables here. And in the case of so in the case of maps, again, we had this guy. In the case of hypermaps with marked and unmarked vertices, we have this a little small generalization of this guy, and you see here we have exponent e to the power g minus 2, and here e to the power of this sum. So here you see that we do not, in the case of just maps, we do not have marked white vertices at all, and all white vertices are unmarked and have valences 2, as I mentioned before, that we put in the middle of each edge white vertex, which are unmarked and has a valence 2. And you see here this j minus 2. Okay, so this is a generalization of the problem to the m endpoint function, but you see here I have this diagonal operator d, just the same as I mentioned for the case of maps. So if we take except of this a certain d any arbitrary function, so we had here, for the case of maps, we had the logarithm of k h bar, and if we take just arbitrary function or formal power series here, psi, then except instead of maps or hypermaps, we obtain generalized double Hurwitz numbers, and the so in which, and this is, you may think about this generating series as a generating series for enumeration of Hurwitz numbers, so ramified covering of CP1 of a sphere by some Riemann surface of genus G with ramification, with some ramification points, and we fix the two profiles over 0 and over infinity, and these two profiles correspond to black and white vertices. So we had some marked points in the profile over 0, and which corresponds to x variables, again in marked point in the profile over infinity, which corresponds to y variables, and we have unmarked part of these profiles, and all other critical points encoded in the coefficients of this formal power series psi. And so in the case of maps, this gives just the third critical point. In general case, we obtain different kind of Hurwitz numbers, like monotone, Buscemi-Le-Chauffer, etc., 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 R-spin, and all known so all known cases of Hurwitz numbers, and many more examples. Okay, so and I have no time, but maybe no, 1 minute. So what is the statement? And I'll stop, and Petra will continue. So the theorem is that if we have a finitely number of t and s variables, and psi and some conditional psi, so that the psi prime is rational, then there exists a change of variables again, that this wmn, some mn point function, is rational in these m plus n variables. Also, we have a inductive procedure to compute this wmn in a closed form, but it's not a topological recursion. It's a different recursive procedure. So with no so not just we use it to prove then topological recursion, but not topological recursion. And then that wmn has poles of in the critical points of x of z and y of z, as in the example, and for the first m indexes in x function, and for the second n indexes in y function. And we allow also there may be poles on the diagonals, zi is equal to zj. And so continue just the formulation of the theorem. So, and for in these conditions, loop equation holds. Loop equations hold for x and y variables, and also this projection property also holds. So under some additional assumption on psi, there are no other poles. So this theorem, that there's how many 6 conditions, state that indeed this wm0 satisfy topological recursion, and w0n also satisfy topological recursion. And this is about, and the last word, duality in the name of my talk, means that this, so we prove that these two topological recursions connect by some duality, which is a generalization of known xy duality in the theory of topological recursion, and we called it symplectic duality because of there are no some deep meaning of this symplectic duality, but you may take some manifold and the symplectic, and take a symplectic form such that they are dual to each other. So thank you. I think I should stop here. Yeah. And happy birthday again. Yeah. Thank you.
Thank you. Thank you, Boris, for the interesting talk. My suggestion is that if there is a short question, then please ask. Otherwise, we will pass the word to Peter. So thank you again, Boris. And our next speaker is Peter Dunin-Barkovsky, who will continue talking on double Hurwitz numbers and beyond. Please.
Okay, thanks. So first of all, yeah, so I would like to say happy birthday to Georgy Borisovich. So I've known Georgy Borisovich for, I think, 17 years, which is a bit less than for many of the other people here, but still, so I've been greatly benefiting throughout all these years from Georgy Borisovich teaching me a lot of interesting mathematics. So I'd like to express my sincere gratitude for that. Okay, so now to my talk. So this is basically a continuation of Boris' talk on the same subject. So based on joint work with Boris, Maxim Kazaryan, and Sergei Shadrin. Okay, so okay, so I will go into a little bit more detail with regard to some statements which Boris mentioned in his talk. So here we have the MM point functions which Boris mentioned. These guys here. Let me remind you that what is the combinatorial meaning of this thing. So Boris introduced all this Fock space notation. This looks like a huge formula and quite unwieldy, but it has some simple combinatorial meaning. So let me maybe using a blackboard just remind for 1 minute just what are we interested in. So basically we are studying ramified coverings of this sphere, and we have ramifications over 0 and infinity. So this is generalized double Hurwitz numbers with markings. So we have some profile over 0, over infinity, and so we have we say that something happens in between. This depends on this phi here. Let me speak about that in a moment. But at 0 and infinity, we see that. So we have looking at this formula in the Fock space notation. So we have these x variables and t variables on the left, and s variables and y variables on the right. And we consider the x and y variables as arguments of this function, or of this as variables in this formal series, which is actually a generating function for some numbers, while so t and s, we consider them as some formal parameters. But basically, combinatorial meaning can be assigned to some coefficient in front of a monomial in x, t, s, and y variables. All of those variables, if you expand this thing as a series and take a coefficient in front of a monomial in all those 4 sets of variables, then it has a combinatorial meaning. Namely, so as I said, over 0, we have some marked preimages of 0 where we have ramification. We have some unmarked points over 0. So so the ramification is controlled in the in the mark points, it is controlled by the powers of the x variables, and in the unmarked points, it is controlled by the powers of the t variables. And the same with respect to infinity and with respect to s and y variables. And then, so for instance, depending on what is this curly d operator, depending on what is this series phi, which Boris talked about, we can have something happening in the at other points. So for instance, we can consider simple Hurwitz numbers for some specific very simple form of this phi, where we allow only simple ramification at some other points. We can have monotone Hurwitz numbers. We can have R-spin Hurwitz numbers, all sorts of double Hurwitz numbers, weighted double Hurwitz numbers, depending on what phi you plug here. And this, as I said, this coefficient in this generating series in front of this monomial is just the count of these ramified coverings, well, divided by the number of automorphisms and assign the meaning corresponding to the to this phi thing. So we'll also be interested in this generating series, which we call H, which differs from W. Just see that it differs just by dividing by K here. So basically, W is what you get if you apply X d or dx times y d or dy over all x and y variables to this stage. Just a bit different form of the generating series. Okay, so and let me stress that for now we are dealing with formal series. So we can have infinite number of t variables, infinite number of s variables, this phi and psi. So this phi is x of psi. So phi is just an arbitrary, psi hat is just an arbitrary formal power series in theta and actually h bar squared. So just for some reasons we have only even powers of h bar here in this psi hat. The only condition is that it should start with theta. So if you plug 0 in place of theta, this psi hat should vanish. This is the only condition. Apart from that, we consider just the case of formal power series, and our first main statement can be made just in this very general realm of formal series. A formal series when everything is considered just a formal series. But to make this statement, so we need to make it precise. We need to introduce this R, which will be a certain ring of formal power series. So we need some condition for the statements to make sense, but it's just the condition that when you fix this R, it's we consider not just any power series in Ts and let's say some other variable x, y, or z, but such that if you fix consider some specific monomial in T and S, then the coefficient should be finite in this additional variable, which is denoted by xi here. And after introducing this definition, we can define what we call the formal spectral curve. So the statement is that there exists some formal series x of z, y of z, and theta of z, such that these conditions are satisfied. Probably don't have much time to explain what is the meaning of these conditions. This formal spectral curve is some analog of the spectral curve you have in topological recursion, or before that, which people studied in matrix models. So, but probably I don't have time to explain this in more detail. And once we have established this formal spectral curve, so recall that this is just some, we have this x, y, and theta are considered as a series in one and the same formal variable z. Then the statement is that if you look at this WGMN, our generating function, which we discussed on the first slide, then it can be know that we have this m plus 1 m, and if in place of this m plus 1's argument, which according to the definition should be x m plus 1, so, but then we need to plug, in place of it, we need to plug x of z m plus 1 according to this formal variable. And the statement is that so that if these series are like this, as described here, so note that they depend on the T and S variables. So if they're like that, then the very surprising thing which happens is that this W, it can be expressed as a finite polynomial in smaller, in this WG prime and prime for smaller m prime and prime G prime according to these inequalities than for the original one. So this can be basically recursively, you can express this generating function recursively in terms of the smaller ones. And it's a finite expression. It's a finite polynomial in the smaller w's and their derivatives. It's very surprising because we considered some complicated infinite formal series, but after this change of variables, which we consider here, everything becomes finite as in this recursive formula. This is very surprising. But this statement holds in a very general domain in just the arbitrary formal power series without any additional requirements. And also we actually have an explicit formula, which I'm not listing here because it's quite bulky, but so it's not just a statement on the existence of this finite recursive formula, but we actually have it written in very explicit terms. I'm just not stating it here. It's quite lengthy. All right, so this is our first statement, which holds in full generality in arbitrary formal power series. Then we have the loop equations, which Boris talked about. Now let me, so I can now say explicitly what they mean, at least the simplest case of the loop, for the simplest case of these loop equations. So in order to establish the loop equations, we already need some additional requirements posed on our psi function, which defines our problem for us. So the previous statement held in full generality for arbitrary power series, but here we need, in order to have loop equations, we need this psi to satisfy some assumptions, which we call the natural analytic assumptions. So basically, this psi without hat, which you get from psi by dropping all terms with h bar, just by putting h bar to 0. So its derivative should extend as a rational function, and for all the coefficients in front of positive powers of h bar, just these coefficients should extend as rational functions. When these assumptions on our power series psi of theta, psi hat on theta and h bar, when they are satisfied, we can prove that we have these loop equations which Boris mentioned. In order to state the simplest case of the loop equations precisely, let me introduce some other definition of this space capital Xi. So this space capital Xi is as follows. So consider just some, so we need to, in order to properly introduce it, it's the easiest thing is to to speak of differentials. So suppose that omega is some differential, and then we have this operator dx, which works like that, where so suppose this omega is some formal differential in this z variable on our formal spectral curve, and then consider this x and y as x of z and y of z as we have defined in the formal spectral curve definition. And you can have this operator. Basically, it is the counterpart for differentials of just the x d or dx operator for this one, and of y d or dy for this one. And then we can introduce this space psi x and psi y. So psi x is the linear span of differentials which you obtain by, it's a space of meromorphic differentials on this, or you can say formal meromorphic differentials on this formal spectral curve, which is spanned by differentials of this form, where you take any holomorphic differential and then apply some number of these dx operators here. So, so this can be actually, when I'm saying meromorphic and holomorphic on this spectral curve, to all of these can be, one can assign some formal meaning just in the domain of power series. I mean, we already have this psi as a rational function, but this still can be extended to series. And this is the theorem which is the simplest case of loop equations. So this is called the linear loop equations. Basically, the differential of this h generated function. Recall that on the first slide we had two different generated functions, w and h, which slightly differed. And if you take the differential of this h, it should belong to this space xi. This condition is actually, so like Boris said, it's this condition, it is a requirement on the principal part of your function. Basically, it has to be it's just a requirement on the principal part, so that you don't have any odd terms with respect to the deck transformation generated by your function x of z. And we also have higher loop equations, which are statements similar to this one, but when you have in the case of quadratic loop equations, you have some quadratic expression in terms of h functions, which should belong to this space, and so on. So for higher powers, we have similar things, and we can prove them in the generality. And like Boris said, this is actually, when we restrict this to the case n equals 0 or m equals 0, this gives you what's called blob topological recursion. So this is one part of the Chekhov and Anton topological recursion. And the final thing is, so in order to have topological recursion, you need to, in addition to loop equations, you need to have also what's called the projection property. Basically, the loop equations said something about what happens at the zeros of dx and dy. It's a restriction on the principal part at those points. And the projection property says that basically you do not have any other poles apart from the poles at these points. more precisely like this. But this statement only holds so you need to impose further restrictions to be able to prove this. Namely, we need to consider some specific family, which is still a very general family of functions phi, where most of the interesting and known from the literature cases of various double Hurwitz numbers and map counting problems, they fall into this family. And you have this theorem that you do not have poles at the unwanted points. It can be proved in this further restricted generality, but still it's quite general. And so, like Boris said, what we have is a new explicit recursion for these mn point generated functions for this very general Hurwitz type problem. And then it allows us to prove topological once we plug n to be 0 or m to be 0. We have two different topological recursions for this, which are connected by what we call symplectic duality. But so I don't have time to further elaborate on this. So I guess I need to stop here. So thank you.
Thank you for the interesting talk, Peter. Are there any questions or comments?
Yes, I have a question, if possible. Could you please, are there some practical applications of your formulas? For example, is it possible to check what Koля told us in the morning? His basic results, okay, he provides the enumeration, but at least the numbers of the results. Is it possible to check by means of your
I think it should be possible. So without,
great.
I mean,
great.
Well, the point is that so our result, if you want to get some specific numbers, so for fixed, say, powers of x, t, x, y, t, and s variables, so like I said here, so this specific Hurwitz number. So this specific Hurwitz number, it can be computed from our formula, so you can use this, for instance, our recursion to obtain the generating functions, and from there recover the specific numbers for specific profiles here over 0 and infinity. But it's probably not the easiest way to do this. So I mean, just doing it directly from I mean, from basically correlator like this, or maybe just writing it in terms of Schur functions and just directly computing this number is probably easier than applying our formula. So our formula is the interest. So why is it interesting? Is that it says that the generating functions have some nice properties. So they, for instance, they turn out to be rational in some sense. So we have some finite recursive formulas for them, but for computing specific coefficients, it's probably not the best way, but it's possible.
Okay, thank you.
So yeah, it's possible, but maybe easier in a different way. Yeah.
As I understand, topological recursion always count. For example, Boris told us that you fix two range patterns over 0 and infinity, and you do not fix the third one. You always compute the sum.
This depends on what you have in place of this phi. So we have indeed. So for instance, if this phi is you're right that this gives you the sum of the possible ramified coverings with fixed profiles at these two points. The sum of numbers where in the middle you have certain requirements, but so the requirements they depend on what specifically you take for this phi. So for instance, so you can, yeah, so maybe I was a little bit too eager to say that you can definitely give the answer to what you had. So this is.
Can you count covers such that there is third branch point and all branches over it do not exceed 2?
So you're saying that just one, you have just one additional point.
Count Belyi functions called dessins or hypermaps such that you have two profiles fixed, and the third profile contains either ones or twos.
Yes, I think it should be possible. I think it should be possible. I can't say this at this point with just 100% certainty. I think it should be possible, but for if you have by taking particular phi here, yes. So there are cases where you have for certain phi you can have any number of these simple ramification points, but I think it should be yes, I think it should be possible to have it limited by 2. Just I think phi should be equal to 1 plus theta squared, something like that. If I'm not mistaken, it should correspond to phi equal to 1 plus theta squared. Psi equal to, sorry, no, phi equal to 1 plus theta squared.
It would be very interesting if we could count such numbers. It will give us exactly.
So if your requirement is that it's not the third point, it doesn't exceed 2. I think it should correspond to 1 plus theta squared, but I need to think a little bit about that.
Thank you. Are there any further questions or comments? Actually, I have one. What will happen if we have not 2, but say 3 parameters or more, which I guess corresponds to 3 color situation or more colors?
So you mean that, so what happens if we fix profiles not at 2 points, but at 3 points, right?
Yeah.
This is the question. So at this point, our machinery doesn't really work for that. So it's actually what we want to develop. So how to deal with triple Hurwitz numbers and further generalizations. But so our current machinery with those correlators, it only works with for the case when you have when you have profiles at just 2 points fixed. So at this point, we don't know how to apply our machinery for the cases when we fix profiles at 3 or more points.
Thank you. Any further remarks, questions? Okay, if not, let us thank our speaker again.
Okay, great. So, may I start? Fine. So, first of all, I would like to congratulate Georgy Borisovich. And I think that I confirmed the most of the things that people said before. But maybe the main thing I want to say is that even I know just Georgy Borisovich just from my very beginning when I entered this life, but still I want to say that he is a fantastic teacher, and mainly because he really can inspire people around him, just really inspired to do everything, but also to do math. And when you listen to him, this is like a music that you want to continue, and you want to, and you cannot even continue it, but if you are interested, you can do a different subject and do still the sounds of Georgy Borisovich continue to be in your mind, and it's really beautiful. And he really inspired to see the beauty of the math, and that's the main point. And I would like to say that yesterday I just make a phone call to my uncle, who was a classmate of Georgy Borisovich, and I asked him if he can also say something. He said that first of all, he wants to congratulate you as well, and second, he also said that he was really inspired by you about the life, that the life is a math, and it's really goes everywhere. So thank you for that. That's really nice. And maybe now I try to continue to do some math that is not really directed to your story, but there are many relationships. And the subject I suggested was the graph complexes, which are also, I think that you like graphs, but also the story is related to the Galois group of the rational numbers. I will not go into that direction, but I will explain you only some combinatorial story around and maybe at the end there will be some theorem, which is a new theorem, and most of the story will be from the previous decade. So first, what is the graph complex? So what are the graphs when I'm thinking of them? So for me, graphs are not related to some surface, but they're just, you consider the graph with n vertices, 1 to n, and graphs nk with k edges and vertices, k edges. And then if you want to do to work with the graph complex, so you have to add the word complex, and this means that you should make the vector space or something where there is a differential. So to do the differential will be combinatorial one, but first you need to say something about the vector space. So my graphs are really the basis or the elements of the story, which you have graphs with n vertices, k edges, and then you should take the invariance. So Sn for which permutes the vertices, so you number the vertices, then Sk that permutes x on edges, vertices, and also we want to add S2 on the S2 to the power k orientation of edges. Now, so you have very simple combinatorial structure, you have graphs. And also, in order to take this Sn, Sk, S2, you see that this in graph complex, there's the extra letter D, where D corresponds to the dimension. D is a dimension. Now the dimension of what? So for me, this is the dimension of the little disks operand. and I don't want to go to that story. But here D corresponds to the grading. So the degree of vertex should be D, and degree of the edge vertex should be 1 minus D. And now Sn, Sk, S2 corresponds, they remember the degree of those stories. So you mean that if, so there are two different cases, when D is even and when D is odd, are two separate stories. So for the case that is related to the Galois group of Q, the D even is the most interesting. The D equals 2 response to Q. Now, what the next thing you have to say is that these graphs, so you have, since the degree is 1 minus D, so this invariance here corresponds to Sn will be, so for D even, Sn x, you have a trivial representation, skx sines, and S2 without sines, also trivial. For D odd, the situation will be opposite. Sign trivial and sign representation. And now the next step is that these graphs, they form, so mark graphs G is a Lie algebra, is a graded Lie algebra with a combinatorial Lie bracket. Gamma 1, gamma 2 is equal to gamma 1, 2 minus gamma 2, gamma 1, where gamma 1, gamma 2 is a substitution of one graph into another. So you take gamma 1, sum over J, you take the Gth vertex of gamma 1, substitute there gamma 2, and connect in all possible ways. So the example will be, if I this works, will be do like this. And here then I erase in all possible ways. So this is this is equal to plus 2 other possibilities. So I'm saying that the set of all graphs form a Lie algebra, and if you consider a particular element, very simple one, this whose degree of this element is equal to, so there are two vertices, 2 plus 2 minus 1, and also need the overall minus 2. This is some extra shift, which I don't want to mention at this point. So it will be 1. So this element is an odd element of graphs 2. And what you can make, you can define a differential is a commutator with this element. If you look more accurate on this differential is what is called vertex splitting. Splitting differential. What does it mean? So that means that if you consider the graph where you have something in the middle, so you have to, the differential will be the sum of vertices. And the differential of a separate vertex will be just the splitting of this vertex in all possible ways. This is splitting. Or you can look on the dual one, the dual map is just edge contraction. Just if you have differential, then the differential will be just contracting sum over all edges just contracting of one of the edges. Now, so this was the definition of about 98 or something like that, given by Kontsevich. And now the next step was done by Thomas Willwacher, who explained why this complex computes many things that we are interested in. And the things we're interested in is just, for example, the first statement is that H, so for D equals 2, H less than 0 of GC D is equal to 0, H0 of GCD is just the Grothendieck-Teichmüller Lie algebra. So the Lie algebra associated with the completion of the Grothendieck-Teichmüller group. And this is precisely the place where you get a lot of relations with the Galois group of Q. And so in particular, Francis Brown explained that that the free Lie algebra generated by sigma 3, sigma 5, and so on is embedded into this GRT. So this graph complex is extremely huge. And you are not able to, and the cycles of this graph complex are really very complicated. So this sigma 3 is the simplest one, which looks like a tetrahedron, and sigma 5 is already a sum of this one plus, say, I don't remember the coefficients, plus something like this. And now, and H1, this is a huge conjecture, is equal to 0. What people know is that so we know that this H0 is something huge. Now we also know that H greater than 0, so this dimension of this is also infinity. But we do not know any kind of inner structure of this graph complex. And each computation for this graph complex is really very, very, very interesting for applications. Also for, so the relation I want to mention is that recently people like the Payne and company, also with Wilwacher and with Galatius, showed that out of the story that they computed something about the homology of MGN of the open one with the top weight filtration and top -2. Filtration. So this was about 18 and 19, and this is just very recently. And now I think because I was started a bit late, I want to add 5 minutes more about saying some results that I want to explain today. Is the story that one more point of view of this graph complex, which was of course very well known, so that if you look on this GCD, so this may be considered as a Chevalier-Lindbergh complex of the Lie algebra of polyvector fields. So the polyvector fields is just the algebra as a vector space is lambda of v times s of v. So you have elements like tensors, like sum of p I1 n d I1 2 n x 1 n n. So this is a typical element of this Lie algebra of polyvector fields. And now what you can say that, so if you look on this Lie algebra of polyvector fields, and you look on the Chevalier-Lemberg complex, and you look on the just the invariant part of this Chevalier-Lemberg complex, then the elements of this invariant part will be precisely graphs where h going this is GC2 just because, so the element of the graphs with directed edges may be considered as a contraction of tensors that you place in the vertices. So this is precisely the element of this Chevalier-Lemberg complex. And now the theorem I want to mention that this polyvector, this T poly, contains very simple, not simple, but the subalgebra of homogeneous vector fields. Meaning that this T poly consists of sum of lambda k v times sk v. What does it mean on the level of graphs? On the level of graphs, you have just the graphs such that the number of incoming vertices, incoming edges is equal to the number of outgoing edges in each vertex. And now the theorem itself, so this was the definition, so the theorem is that the Chevalier-Lemberg complex of this T poly is quasi-iso. So have the embedding in the opposite direction. T poly 0 of the homogeneous part. And this, so this is the theorem of myself and Sergei Merkulov. And it has very strange application. Which I just only mentioned. And the application is that the story of this story about the Chevalier-Lindbergh complex of polyvector fields comes from the story about quantizations of Poisson structures. And now the corollary is that the quantizations of quadratic Poisson structures is an exact representation of GC2. So that this graph complex, it acts on all possible quantizations. And if you look on the quantization of the Poisson structure of the linear Poisson structure, then it's nothing interesting because it's the only thing you get is just the universal enveloping of the Lie algebra. But the quadratic structure is already something interesting. And the statement is that all interesting that you can find is already can be cached on the quadratic story, on the quadratic Poisson structures. So this theorem is not really something that you can, something amazing, because you know that more or less every algebra can be interpreted in terms of quadratic relations, but the story of graph complexes here is really something strange, because you can relate two different kind of graph complexes and show that they are quasi-isomorphic because of some computations, and the result will be something like this. So all this, what I want to say at the end is that all this is just different attempts to understand this graph complex. So we still don't know very few things about this graph complex, and this is just one more attempt to the story, just one more realization of the story, and there are much more that people can find, but still no general answer. Okay, so I think I have to stop.
Thank you, Anton, for the interesting talk. There is a time for a quick question or comment. Okay, if this is not the case, let us thank the speaker again. And proceed with the last talk of this session by Alexander Voronov, and he will talk on the BV structure on the cohomology of moduli space. Please.
Thank you very much for the introduction and also for inviting me. Do you hear me fine?
Yeah, we do hear you, but and now we see your screen as well. Yeah.
Yep. Somehow it's in the middle.
Somewhere in the middle of the room.
Not actually so many pages, but it's repeating one page several times. Okay, so I will be talking on the BV structure on the homology of modular spaces, and it's a joint work with Sumeira Sakali, who is at the University of Arkansas, and I'm glad I'm able to speak in this conference. I always appreciated what Yura or George in English has been doing in mathematics. And in particular, he was always fascinated with the modular space and their cohomology and homology. He has written several papers on that, but moreover on the Sandan Fong, and I think that Eura has inspired people, a lot of people, to study this theory. In particular, I remember when I was in graduate school, Eura had a remarkable student, not an official student, but a factual student, and that was Volodya Voyevodsky, who was very inspired by the son Anton these days, and this inspiration came from Eura. So let me start my talk. I will be talking about, as I said, moduli spaces and their homology. So let MGN be the moduli space of connected compact genus G Riemann surfaces with n-labeled punctures. Yeah, and suppose that, yeah, so this is the moduli space of Riemann surfaces or algebraic curves, and so it has been mentioned several times here, for instance, by Anton in his previous talk. So that means I should be pretty brief on this. This is the moduli space, but we consider the moduli space with n unlabeled punctures, which may be thought of as the quotient of the standard moduli space MGN with n labeled punctures by the symmetric group. The punctures. We all know the dimension of this space for genus high enough, and the rational homology of this, even the rational homology of this space and its dual, linear dual cohomology are very very poorly understood. So, for example, let me mention a few results that stand out. For instance, the Mumford conjecture, by Edson and Weiss in 2004. Faber's conjectures, which are still only partially settled. I misheard something. Okay, yeah. So then Eura's work in 2015, for example, with Tunin, Barkovsky, Popolitov, and Sliptsov on the homology of modular spaces with level structures also offered some way of a very subtle way to compute the homology of modular spaces with level structures. And but it's still a very tantalizing space. Nobody really knows the topology of it. But a lot of remarkable facts are known. For example, stability of homology and cohomology. Okay, so these are the main players I will be talking about. And but on the other hand, I want to bring in something that came from physics, from quantum field theory. And this is Sen and Zwieback work of 1993. They studied string field theory in relation to string theory, and they discovered that it yields a BV structure on the homology of those modular spaces. So it's you basically pull together the homology of all modular spaces for all possible genera and the number of punctures. And then on it, they discovered that if you take this space, you can define a BV operator and an anti-bracket. So a BV operator is, in a certain sense, a second order differential operator if you do it on the homology of modular spaces on the dual space, but on this space it also exists. And an anti-bracket provides it with a structure of a graded Lie algebra, certain shift in degree. But it doesn't really matter. These are two new physically modulated algebraic structures as compared to standard structures. For instance, on for each G and N on the homology of this modular space MGN, one can have the structure of co-algebra, or on the cohomology, the structure of commutative associative algebra. And these are structures that actually always help us to understand and to compute or to write down in a closed form to describe in a closed form the homology and the cohomology of the modular spaces. But these two structures, they actually, this is why we sum up over the genera and functions. These two structures are algebraic structures, but they are between, they happen between those spaces, modular spaces. That is, they mix the genera and the number of punctures. I will tell you later what they are. Now the quantum, in a few seconds. So the quantum master equation is another feature of the theory. It says it resembles the Maurer-Cartan equation, but it has an extra quantum term, this h bar delta s. The Maurer-Cartan equation would be without this h bar delta s. In a sense, this is also a Maurer-Cartan equation because you can unite the first, pull together the first two terms, and this will be still a differential. So you can view this equation as a Maurer-Cartan equation, but of a specific type. And this is an equation on chains S. So S here is a chain, well, actually depending on some variables, some formal variables. Usually S is S of lambda h bar with coefficients being chains in, so the coefficients are chains. So it's an equation on S with coefficients being chains on in various modular spaces. So for physics, it's an important equation you can judge by the name, the quantum master equation, and it's related to some kind of solving quantum field theory non-perturbatively. So basically, if you are able to solve this equation, then you know how you are able to reach sort of a more complicated non-perturbative quantum field theory. And for instance, a remarkable work in this regard is a work of Kevin Costello in 2009. He proved that a solution of the quantum master equation with a natural initial condition exists and is unique up to homotopy. This is still an introductory part. I'm introducing the main characters. I have been introducing those like the modular space on homology, and here is a new physical structure on homology. Okay, so the goal of my talk, of my work, is to relate the BV structure with the topology of the Belyi-Mumford compactification, MG and bar, and prove a vanishing theorem for the BV operator delta and the ending bracket, and provide a counterexample to a physically motivated conjecture. So why is it interesting? Here are reasons. First of all, any general theorem of the structure of this mysterious homology of modular spaces is interesting. So this is kind of a cheating answer to this question, but as I said, the homology of modular spaces is a tantalizing subject, and even any general theorem about the structure of it would shed some light on it, on the homology. Now, the second reason for being interested is a vanishing theorem of the type that I will show you later may help to solve the quantum master equation non-perturbatively in the spirit of Costello's existence and uniqueness theorem, and possibly simplify his argument. So and simplify his argument. Okay, so I'm going to pursue those goals. So first, I want to describe the BV structure and on the homology of modular spaces and related to the Belyi-Mumford compactification, to the topology of the Belyi-Mumford compactification. First, let me start with topology. So the topology of the Belyi-Mumford compactification, the part of the topology I would be interested so far in the beginning is pretty simple. It's this topological filtration by the topological type. So of the Riemann surface, of the stable, that is singular Riemann surface that we are dealing with. So take the Riemann compactification here again. It's the modular space of algebraic curves of G, the n functions which are unlabeled, and we consider them the Riemann compactification of this modular space. So it becomes modular space of stable algebraic curves of G with n unlabeled functions. And then this component of filtration, the pth component of the filtration here is the modular space of stable Riemann surfaces with at least p double points. So it will be, I will sketching. My pictures will be more like pictures of Riemann surfaces rather than algebraic curves. Let me keep this. Functions. Okay. And this is a double point. So this will be a point in the modular in the piece of filtration corresponding to this number p equal to 1. Okay. So we take this topological filtration. The more points you get, the more double points you get, the deeper you are in this topological filtration. And then, as always, a filtration of a space creates a spectral sequence. I think this spectral sequence is called a topological spectral sequence, corresponding to this topological filtration. Its first term, where the sequence of cohomology is the cohomology of the complements of two subsequent pieces of filtration. So you take the complement of this subspace in this space, and the sequence converges to the cohomology of the compactification. It has the differential d1 dq. For the first term has a differential which goes like this, and this is given by one can describe it in several ways, but one of them is you take the Poincare tool of the boundary map and the lambda sequence of triple valued subsequent terms of filtration. This gives you the boundary map. You write it using Poincare duality. You take it the boundary map and the exact sequence for the homology of the triple sequence, but then you apply Poincare duality, and you end up with the homology of those complements, or the cohomology of those complements. Like this. So this is the first differential in the first on the first page of this spectral sequence. And actually, this map, as I said, it may be described in several ways. This differential, it's actually the Poincare residue map. It's some kind of Giesen map in this sequence. Basically, integrate. One can think of it as integrating over the fiber of the tubular, not the tubular, the bound. You take the boundary of the tubular neighborhood, so it's called. I think the spherical neighborhood of this smaller subspace, and you take the spherical neighborhood of this space in this ambient space, and then you integrate over the fibers of this projection, of the projection onto the square. And so you use, it eats up one cohomology degree, and this. So it's basically this is a divisor in this complex codimension one, and so this piece of filtration, and so it's also known as Poincare residue map. Okay. Any questions about this? All right. So we continue the topology. As I said, I will be mostly looking at the homology. I will be describing the BV structure of the homology of the modular space. And here I started with cohomology. But the thing is that I will also be considering the linear dual map to this differential in the cohomological spectral sequence. And this is just a linear dual map. It's also some sort of Giesian map in homomorphism and homology. It notices that it increases the degree. So you basically acquire back this circle fiber of the bundle, of the spherical bundle of this, subspace in that subspace, of this divisor in this space, in this stack. Okay, so so far so good. I will be using this dual, linear dual hybrid D1 to Q star later on to describe the BV operator. So the BV operator and the anti-bracket, those physically motivated ingredients, well, they're physically motivated, but actually they are related, and this is probably related to Anton Khoroshkin's talk. They are related to the modular operand structure on those modular spaces. Well, on the modular spaces with labeled functions. But here we unlabel them with the BV operator comes up, but still out of the modular operand structure on mg, m. Okay, but it showed up in physics first of all, the structure. So the first is just a linear operator from hk to hk plus 1, the BV operator, and it goes like this. At the level of points, the map is kind of induced by at the point level, but not quite. It's not induced by not induced by any continuous map between modular spaces, because otherwise it would preserve the homology degree. But actually, it increases the homology degree. But still, it's possible to describe it. So basically, if you think of a representative of this homology group as a K cycle, which you think of as a family of Riemann surfaces. So suppose we have something like this, Riemann surface like that. And so what you do to define this operator is the surface has n plus 2 punctures. It was genus G, and you pick sum up over all pairs of punctures. So you pick 2 pairs of punctures, and then you cut out those little disks around those 2 punctures. So you sum up over all possible pairs. So given a pair, you cut out little disks around about those punctures, and then you glue the surface at those disks so that it becomes like this, a surface like this. You glue the surface along those disks so that it basically requires an extra handle. But you do it also this way is an operation on the modular space that goes from mg n plus 2 to mg plus 1 n. So this is a point in mg n plus 2, and this is a point in mg plus 1 n. But what you also do at the same time is you insert a twisting of solving. So before solving those 2 boundaries of those 2 disks that you cut out on the surface, you also insert all possible rotations before so insert all possible rotations of the boundary of one of the disks. Boundary before solving. And this, how many rotations are there? It's S1, so you insert an S1 worth of rotations, and this way you create out of a k-dimensional chain, you create a k plus 1 chain out of a k-dimensional family of such Riemann surfaces. You create a k plus 1 dimensional family of surfaces of genus G plus 1 and having n punctures, you hit up 2 of those punctures. The anti-bracket is similar, but it happens not on one Riemann surface, but on for 2 Riemann surfaces. So, for instance, suppose you have 2 Riemann surfaces like this, and so it goes like you take possible pairs of punctures but one on one surface and one on the other Riemann surface. And then you solve them in a similar way by cutting out little disks around those punctures and then doing all sorts of twists. That's just one worth of twists. And this will be the seam, and then you again insert all possible rotations before so here too. And this creates an operation from going from the K1 homology group of the first modular space tensor to the K2 homology group, second space to the K plus 1, K1 plus K2 plus 1 homology group of the space whose genus is the sum of the genera as the number of functions n1 plus n2. So these are two operations, and they are actually also typical for modular operas, but here the thing is that we unlabel the punctures and we sum up all with a certain sign using the notion, a certain notion of orientation. We sum up all possible solvings of that. Okay, all right. So first of all, I wanted to, these are those BV operators. I won't be talking in detail about the anti-bracket, but because it's similar and there are similar statements, you can look up on the internet. But let me just talk about the BV operator. So this proposition that describes the BV operator that I just described before. Describes it as in terms of the differential of the dual map for the differential of that spectral sequence of that topological spectral sequence on the modular space. So this is this. The statement is that the BV operator is actually maybe described as a certain composition using this differential in the spectral sequence map. The first map is coming from the attention map. So instead of doing solving, we attach things. And let me do this. Let me describe it on the next slide. So the statement is that the BV operator may be described as a composition of this differential in the spectral sequence. We showed up here this dual, linear dual of the differential for the first page of the spectral sequence. And the composition with a certain map alpha, which doesn't change K. So it's a simpler map, and it actually almost comes from a topological map. It comes actually from this diagram. And this alpha map is the attention map. So here we consider the modular space of labeled pairs, of labeled Riemann surfaces or algebraic curves with n plus 2 labeled functions. But we model it by the action of Sn and S2 of those symmetric groups, S2 acting by permuting the last two punctures, Sn acting by permuting the first two punctures. And so we basically unlabel the punctures, but we basically divide them into two groups, a group of n punctures and a group of 2 punctures. And then there is a natural further unlabeling that is forgetting this division into two groups, projection onto the modular space with completely unlabeled functions on the one hand. On the other hand, there is a map, the attention map. So this attention map, it takes a Riemann surface on which you divided the functions into, there is a division, so we are defining a map pi on this space. So there is a division into two groups of functions, and the first n and the last 2. And when you take the last 2, what you do is you this map pi that does the following: it attaches the two punctures together to create a double pole. So what you get is you can think of this as the following process. Then you So you pull out those two functions and then you attach the two pieces of the Riemann surface. And those functions creating a singular Riemann surface with a double point instead of those two functions. And this places you in, if you start with, so here we are not doing the compactification, this is the open modular space, and then you get a singular, so it's a non-degenerate, non-singular Riemann surface, and then you get an element in the first piece of the filtration. You acquired one double point. And it's not, and you haven't acquired two double points on this device. You want to do this complement of the first piece of the filtration minus the second piece of filtration. And then you can take, for homology, you take the map going this way. That is, you take the transfer map against this map because it's a finite projection. This is a finite map. And then you map to this and push forward to homology, so you get a map. And this is the other ingredient. So basically, we have this theorem, this proposition decomposes or explains how to define the operator delta in more algebraic terms, in more algebraic geometric terms, I would say, because there we were cutting out some disks, and for instance, we were interested in homology. It didn't matter which disks we would cut out, as long as they're small. But here, everything is more algebraic, right, with differential spectral sequence, and this attention map is very algebraic. Belongs to the realm of algebraic geometry. Now, the vanishing theorem that I wanted to mention, actually, I think my time is up, but this is the second to last slide. Is my time up? Yeah, so the vanishing theorem that I want to mention is that there is some vanishing for this BB operator and a similar statement for the anti-bracket on homology of modular spaces. So there is a pretty good range of vanishing of this operator that it vanishes for a large enough degree in homology. And this is basically because the homology is zero for a large enough degree. This comes out of Harar's old Harar's zero on the homology of the modular space. And then this is the stability range for the homology of the modular space when the degree of homology is little as compared to the genus of the Riemann surface. Then this is the stability range, and in the stability range, the delta is also the operator is also clear. There is a similar statement for the anti-bracket. So this is a pretty simple theorem. As I said, well, actually, it comes out of the Harar's bound of the homology of the space, and this comes out of the stability of Harar. Well, here I'm using the improved bound by Nikolai. So actually, it turned out to be more complicated just to construct a counterexample of the conjecture. So the physical conjecture that I mentioned is which existed but is no longer there. Delta is zero on the whole of knowledge. And actually, it turned out not to be true. No, this was a good piece of evidence for this conjecture, and also there was some physical motivation for it. There was some kind of formality related to this at the level of differential graded algebras to the vanishing of this operator. So if delta happened to be equal to zero to vanish on the whole homology of the modular space, then it would be some formality statement in relation to this Maurer-Cartan equation. But actually, it turns out not to be true. So the BV operator is, here's an instance of the BV operator which doesn't vanish. And it's related to the homology of modular spaces in smaller degrees. And actually, this operator is in isomorphism in one-dimensional vector spaces, H5 of M22 and H6 of M3. And this operator is an isomorphism, so it doesn't vanish. Actually, it was this theorem is hard to prove because you need to engage Hodge, like mixed Hodge structure to prove it, and some known computations by Louis and people, Tamasi, and Dan Peterson of those homology groups in smaller degrees. That's all. Thank you so much. Congratulations, Yura, again.
Let us thank the speaker. And the talk is open for discussion.
Can I speak?
Yeah.
Yes, please.
I'm Gabino from Spain. Can you hear me?
Yes, we hear you, please.
Okay, so first of all, I like to congratulate George on his 70th birthday. So congratulations. Well, I have a question about this talk, really. I'm not familiar with this material. So can you please go back to the very definition of this BV operator? That is, it seems to me that at some point you associate, the first, you associate, that's it. You associate to a Riemann surface of genus G with 2 points. Somehow it seems that you associate to it a Riemann surface of genus G plus 1.
Yeah.
You forget about the points and create a handle or something, right?
Yep.
This is it well defined that this is not topological, right? This is the Riemann surface of genus G plus 1 will have a Riemann surface structure. I wonder whether the handle is well defined just by the information of the Riemann surface of genus G you started with and the 2 points, because the handle can vary on, I don't know, the diameter, or could be, right? I don't know if I transmit my doubts. I'm not familiar with this.
You have absolutely valid doubts. So there is no, and this is why actually the theorem of describing the BV operator in algebraic terms was made sense to describe it this way, because that way it's not coming from a map which doesn't exist, and the map which doesn't exist is this map, mg plus 1 n. There is no map like this, even though it may look like it. So there is nothing like this.
That's what I was thinking, that this is not clearly the map, but you are talking about a different thing. Right?
Yeah, I'm talking about creating a map on homology. And so for that reason, you see, if we choose a slightly different disk, we are choosing 2 disks. They may be, well, we can choose holomorphic disks on the in some local coordinates, around those punctures, and we can choose holomorphic disks and then glue the surface holomorphically. But remember, we also insert this twist around. We can still do this, and this would create like an S1 family parameterized by S1 of those Riemann surfaces. But this depends on the choices of those disks. But if you two different choices will be homotopic to each other if those
different
disks are small enough.
Then twist is what you're saying.
Yeah, we are inserting.
Will be homotopic,
it will end
doesn't
up,
matter on homology. That's what you.
Right. It will be a Dane twist already for the glued surface. Like for the glued surface, it will result in a Dane twist. So we are inserting this. But Dane twist is just a twist by 360 degrees, and what we are doing is we are inserting all sorts of twists, like for at each angle, and this increases the dimension of the family. So if you think of a K chain, or K cycle in the homology of the modular space as a K-dimensional family, well, parameterized, say, by a singular simplex, if you wish, a K plus one as a K-dimensional family of such Riemann surfaces. And then you pick disks in whatever way you want, but you remember that the choices are homotopic, are defined up to homotopy, and then you create, you make all sorts of twists, and then you create a K plus one dimensional family of such Riemann surfaces. And this is well defined. This is how physicists define this operation.
Okay, thank you. I think I understood a little bit.
Yeah,
Great.
Yeah, and then the theorem describes this in more algebraic terms using the spectral sequence differential and the attention map, which is algebraically which is well defined. You have this diagram of maps with this map row being finite, and you then but those maps are defined even in the algebraic category. They're defined for stacks. The attention maps. So it's the attention map.
Yeah. My mistake, as you said, is that I was thinking, as you said, that you were defining a map from a modular space of genus G to the modular space of genus G plus one, but you are not doing any. You are not doing that, right?
Well, in this case, we are. In this
I
case,
made
we
a
are.
mistake. Yeah,
This
I
is
understand.
not,
Right?
you haven't made a mistake, because in this case, we are defining a map. The attention map is there. It's just that the gluing map is not defined. But this goes from a Riemann surface of genus G to, or an algebraic curve of genus G to an algebraic curve of genus G plus one. But it's a singular algebraic curve. It acquires a double point.
Yeah. Yeah. Okay. Thank you.
Thank you. Yeah.
Thank you. Any further?
I have two small, perhaps, questions. The first, Sasha, thank you for a very interesting and informative talk. And then, as for your last counterexamples,
yeah,
concerns the curves of a very small genus, 2 and 3.
Yeah.
Does this isomorphism you used to do this state that the conjecture was wrong, does it has any direct geometrical meaning? We seem to know almost everything about M sub 2 and M sub 3.
Yeah.
Are there any hypersurfaces making geometrical sense that give the isomorphism you discovered?
I can't say in those words. Let me see. I'm not sure I know the geometric meaning of that. I was using, I know that we know the homology of those spaces, but the question was whether this map is non-zero in homology. And what I was using was the Poincaré-Serre polynomial describing the Hodge, the mixed Hodge structure, like the weights of the Hodge filtration on the homology of this modular space. I don't know actually of
geometric. Just totalizing together with 5, so it is something about some hypersurface in the modular space.
You're talking about the five-dimensional surface, right? And 6-dimensional surface. Yeah, that's an interesting question. I don't know how to interpret this in terms of hypersurfaces in those modular spaces. No,
okay.
Sorry.
And the other question is whether all these operations you spoke about are somehow consistent with the known cell decompositions of moduli spaces labeled by the sense, with all this story of
are you talking about cell decompositions given by graphs, like ribbon graphs, or
yes,
dessins d'enfants? Maybe I see. I don't think so. I don't think that any of these operations are really.
Can they be restricted maybe to the?
They might, right? But let's see.
Well,
yeah, maybe actually, that's a good point. Maybe they are. Oops, I'm looking at the wrong page. Yeah, so you know, if you are looking at this attention map, it might be nicely related to the to those. Yeah, it should be. It could be somewhat related to the ribbon graph picture, right? Because basically you're not doing anything to the surface, and you basically are attaching two punctures on it. So in this way, it's fine. But on the other hand, the topological filtration map, I don't know how it would be. It would be. I mean, the differential in the spectral sequence map. I don't know if one can define it at the level of those cells. That would be basically to define it at the level of chains. But on the other hand, of course, if you have a spectral sequence, you can define the differential at the level of chains if you're lucky. So I don't know. Good questions.
Thank you.
May I ask a question as well? So it's yeah. So also maybe partly a comment to the question of George. So, but there is, I mean, because so if you want to define the operator delta, I mean, the most natural thing for me would be to use what people call these Kimura-Voronov spaces, right? So the real orientable blowups. And so then delta would end up on some boundary component of this real compactification.
Yeah.
Right. And for that, I think so. There is a model. So these graphs with black and white edges and so decorations like distinguished hooks or edges, right? So this is the one that is used, for instance, in the recent paper of Castello, Calderaro, and Tu. And so I think that this is exactly the description that, I mean, it gives description of delta as it would be using so your old model for the definition of delta, right? But it wouldn't be a description through this spectral sequence algebraic formalism. So, and in this sense, it's so my question, but maybe it's not a question that anybody can answer at the moment, is whether these two can be related in any direct way.
Well, actually, I think this BV operator, of course, is the same operator as the one which is described by using the KSV compactification. You're right. Yeah, it is the same. Like if you use the fact that it's homotopy equivalent, that this compactification is homotopy equivalent to the modular space itself, to the open modular space, then you can use this equivalence to see that delta is the same. Yeah, so you're right. Yeah, it seems like indeed you can use define those things at the level of cells. Thank you so much for mentioning this work.
No, but also because it would be then it would be also an answer to the question of George, because then I mean so this description, I mean I think it goes back to Kontsevich Soberman. So it gives description of your compactification. Actually, we saw with additional framings at all marked points. So it gives a cellular decomposition by also a kind of this Streber graphs, just with a bit more decorations. And so the operation delta there is then defined purely combinatorially. So by a very similar composition rules as what was in the talk of Anton.
So you mean it answers which question of George? The question about
so whether I mean it doesn't answer the question whether two steps of your construction can both be described, but that the total results can be described in terms of graphs explicitly in combinatorial way.
Yeah,
this does.
It seems like it. Yeah, absolutely. Yeah. Thank you for the comment. Yeah, Sergey. Yeah.
Okay. Any further questions or comments? if not, let us thank our speaker again. Thank all the speakers from today and especially from the last session. And finally, I would like to say that I've heard everybody is impressed by the inspirational mathematics that Georgy Borisovich is doing. And I would like to add that I am really impressed by the diversity of topics as well. So many interesting subjects that your school, your endeavor is studying, and the topics that you are doing is just amazing. So thank you for that diverse, inspirational picture of mathematics from today. And okay. I think now we are going to close our session, and participants who are in Moscow will still be together.
Yes, that's it. But one more undertaking was planned. Due to the time constraint, it is going to be as short as possible and is called general discussions. However, let's spend a bit of time to it. Well, first of all, I heard lots of kind words today, and I was unable to react at them individually. So let me generalize a bit and just say, dear friends, it is really touching and giving a feeling that, well, the long mathematical life was not quite in vain. And then the idea was that since the speakers were rather limited in time, we would give some opportunities to add things or say some really general words about really diverse mathematics we were discussing today. Well, perhaps we can do it tomorrow in the form of concluding remarks, but the problem is that we are not going, not all us today will be present. So then, until tomorrow, everybody, and we really close.